Hi everyone. I can see you guys on the side. Unfortunately, I can't make it. And I'm Hongyang Li from the University of Hong Kong. And today I'm gonna deliver a talk on the end-to-end autonomous driving, past, current, and onwards. So my talk consists of four parts: the introduction, and also we propose a conceptual level idea called the word engine, what we call the end-to-end tool. And also, my talk will involve recent progress, including three recent works from our group about on the scene generation and also multi-traversal Gaussian splatting for the scene rendering, and also how to fairly evaluate or benchmark the autonomous vehicles reliably. And the last part deals with some key challenges on this field. So the definition of the end-to-end auto driving, so it's learning a single model that maps the raw sensor input directly to the driving scenarios, and it replaces traditional modular pipeline with a unified function. So here the function means given the observation or the target goal, we directly output the control. And here, the observation, you can say the image, the point clouds, or the vehicles, right? And the controls, it deals with the steering or brake or throttle. So the training pipeline is very simple. You can either use supervised learning with many annotations, or you can say the imitation learning, or using the design the reward and use the reinforcement learning. Okay, so here is a setup. And also we draw a very straightforward pipeline roadmap. So we can call it in the early days, I believe this dates back to the more than 20 years. So it's a very simple input from the black image drive-by-wire interface. And also through the years, we can see a bunch of methods. You can group them into different categories, whatever is a conditional imitation learning or generalization or the other interpretability where the network uses multimodality from the Andreas Geiger's team. And also we have the PPGL and also self-D ACT, ACO, they all works on the pre-training stage. So until recently, we have some explicit methods where the modules are still explicitly designed. You have the tracking, you have the mapping, and also the planner. But this is where we call the modular end-to-end planning. So for more details, you can check out this fantastic survey paper here. Of course, this is an incomplete list. Past years, so we're all working on the for the end-to-end like 1.5. The reason we want to name it 1.5 is roughly defined by the number of corner cases resolved. I mean, so obviously, autonomous driving, the research has entered into the second stage where you're going to deal with massive amount of production issues, engineering efforts, right? So since the work of Unit 80, I could roughly say that we enter the era of foundation models. So the most foundation model, the upper level, deals with the diffusion or using the diffusion pipeline and also the word models. We can see the drive dreamer, or we can see the Cosmos Predict 1, and also the navigation word models. I believe this is year's finalist paper, right? And also the GenAD Vista paper, they utilized given the multi-view images and given the different actions to predict the different types of videos to generate realism and also the diversity. And also we see the Gaia 2, which is video generative models for safer assistance and automated driving. And in the lower part of this slide, we have seen a lot of LLMs. For example, the Drive LLM, they propose a graph VQA to get a better understanding of the driving scene, and also the Lingo tool, and also this Drive VLM. I believe this is a very early work for the dual system in auto driving, where to utilize the better accuracy of the foundation model, but it has a heavy latency, right? So this is where the smaller model steps in to predict, like for most cases, and the both two systems leverage together. And we also see some examples in the robotics, right? And also this same lingo, I believe this is a very recent work, closed loop driving with language. So what's next for the end-to-end auto driving? I mean, if we could define the second generation. So the development here, we show the stack of driving models. This is a typical training and deployment pipeline where you got the data collection part. It's usually driven by the experts, and you collect the data, got to the training stage, and you train on the fixed log and play. And also you got the evaluation, and you have many feedback rate from the inference and collect more data, especially for the bad cases. So the question is, can we collect all the corner cases or edge cases, you could say that, and make it really a product towards the L5 or L4 eventually? So here we have some facts. I really like this website. I believe many of you come from the industry and also see the website here. It's called the Tesla FSD tracker. Basically, it collects many customer data on the website, primarily in the North American cities. So this figure shows the distance to the critical disentanglement of Tesla FSD over the different versions over the years, right? So you can see the MPI got increasing, which is very promising. That's good. But here, this is a figure. I think this is a motivation from the our recent work, recent project called the word engine. So here, the x-axis means the normal driving and also safety critical or near miss events. And if you drive very far away here, you're gonna run into the accidents. And the y-axis shows the we have two y-axis. The black curve is the occurring probability per mile to show the dangerous cases. And also, you're gonna see the red here is the deployment cost. So as we enter into more, like most perception problem have been already resolved, right? So the chance of uh, running into the challenging case become very rare, but the deployment cost becomes very expensive because you're gonna have a large fleet to collect all the dangerous cases, right? So we argue the remaining 20% of long tail problems require an excessive amount of data. So the reason is, can we collect all the corner cases? I mean, valuable corner cases become increasingly rare, and collecting data on dangerous driving can risk lives, right? So here we have this very, yes, the very conceptual pipeline called the word engine. This is a very high level concept level figure here. So we have the data collection. We want to learn from the human, right? So learn from the expert driving. So the policy is still the end-to-end planner, whatever is UniAD or VAD or other end-to-end given an arbitrary end-to-end algorithm. And through the environment with the vehicle, you can use call it the word model or engagement with the environment given the current prompt or actions, for example, turn right. We want to learn from the failures and improve the current end-to-end planner and make it shapeable for the production. So the key question is how to generate these value corner cases. The very key part here is to I think consists of two parts. So here, this is a corner case generation. Given the source scenario from the raw data, we want to generate the safe critical scenarios. This is a generated part to saving a lot of cost if you don't have a large fleet of cars. And this is on the behavior level of word model. Basically, it means given the trajectories, you want to model the behavior modeling between the environment and with your ego vehicles. And then once you have the trajectory, you want to render the things. This is what we call the generated or rendered rendering videos. So this is a sensor simulation. So through this feedback, we have this data engine to generate a lot of corner cases scenarios. And then we have the algorithm engine, which is not drawn here, is simply because it's work in progress. So altogether, these two parts, I mean, the data engine and also the algorithm engine consists of the word engine whole pipeline to improve an arbitrary, I mean, the end-to-end algorithm. So the third part, I'm going to go into the details about the recent progress as to the data engine part, where we have the scene generation called Nexus and also the MTGS multi-traversal Gaussian splatting. So here, this work is called Nexus, decoupled diffusion sparks, adaptive scene generation. So the task here is given map information and also the historical full scene agent states. So the agent states can be the trajectories of the agent from the past. The output is to generate the future agent states. I mean, the states can be waypoints, velocity, or dimensions, or you can simply imagine this is a motion prediction or trajectory prediction task. But here we want to argue that the key challenge here is so the synthetic scenario generation is to balance the reality and also the control. So this is we start from a simple diffusion policy. So as you may know, so the full screen so the full sequence denoising is gonna achieve the goal orientation. I mean, it has a very clear target, but are rigid and cannot react to dynamic environment changes. And we also have this next token prediction. This is another pipeline lineup of work, so which resembles GPT-2. You have are very reactive to changes because you predict the next tokens, right? But can easily lose track of the long-term goal. So we want to combine these two properties, which is reactivity and control here. By assigning each token in the sequence an independent noise level, we can treat them differently during the generation, which we group them together, group them into two categories, which is low noise tokens, provide strong guidance, ensuring long-term control. And another group is the high noise tokens, grant freedom to adapt, ensuring real-time reactivity. So here in the Nexus, we want to bridge the gap between the reactivity and also the controllability, reacting to real-time changes, while also the agent knows the whole long horizon. I mean, in this term, the predefined goals, the target point you are gonna go. So as to the framework for this goal orientation, we have the agent tokens are encoded with time and denoising steps. And then they interact with the maps and the dynamics via the attention. I'll skip the details due to the time limit. So, in a nutshell, Nexus uses a diffusion transformer and also the schedules tokens with varying noises level to control the generation process. So here, this is a very brief report. So we can see Nexus significantly improves planner performance and also the simulation realism in terms of ADE or other metrics in the motion prediction part. So Nexus full means we also generate so the whole experiments are done on the new plan datasets, and also we specifically generate a lot of more training data deals with the safety concerned properties. So this is what we call the Nexus full. So basically you can see this is trained with a larger training data sets. And visually you can see this is a scene that the Nexus generated as the corner cases. For example, here a vehicle overtakes from the right rear of the Eagle car and moves to the front. And also another work is called the multi-traversal Gaussian splatting. So this task is very simple. So basically it's a reconstruction from the single traversal. It's limited. So we can see we have the original view, existing work on the driving scene reconstruction suffer from the view extrapolation. So the main reason is forward motion, less view constraint, and also the repeated texture. So how are we gonna solve this? So here, this is a teeter figure in the original archive paper here. We just released like 3 months ago. So multi-traversal data from daily commutes. I mean, for the single pathway, like from your work to your daily home, right? For the same road, you can commute multiple times. So we can collect this data as the effective view interpolation cross lanes. But there's going to be lots of challenges. For example, the various appearance as in the shadows and the light, and also the transient dynamics. For example, the moving, the parked vehicles. So here, okay. So these are the results. Uh, these are the pipeline here. We have the multi-traversal data and also the LiDAR guided exposure alignment, and also the other training part, like how are we going to utilize all the losses to reconstruct the scene. So first, we will have this reconstruct a scene graph with a shared static mode. And also we have this appearance mode applies to the traversal specific appearance effects. And also we got the transit nodes, put the cars on the ground. These are the visual results. We can see here is the MTGS results. You can see based on different training segments, it can reconstruct scene with very realism, and you can traverse with a large space. I mean, across even to 10 meters from the right to the left. And also deals with unseen scenario. You can see those are all generated scenes based on the losses or the other pipeline I just briefly mentioned earlier. And also, this is a visualization of the high-risk scenarios generated from the Nexus. And the last piece of work is the pseudo simulation for autonomous driving. So this is a collaboration work from the Andres Geiger, NVIDIA, and Bosch, and our team. So basically, what do you mean by the V2, the second version of NavSim? So here we observe that open loop evaluation, especially is on real data. This is a good part. And also it's compute efficient, no sensor rendering, and allows parallel model inferencing. But the downside part, it doesn't model compounding errors, right? So this is basically the very essence distinction between the open loop and the closed loop. And it also doesn't model the causal confusion. So here, for the closed loop evaluation, the good part is it models compounding errors. Subsequent inputs become very challenging with poor initial actions. And also it models a causal confusion. So historical motion insufficient for planning, but it's on the synthetic data and it's compute intensive, which means it requires a sequential sensor rendering and also requires a sequential modeling inferencing. So we want to merge these two parts together. So this is why we propose the pseudo simulation. So the pseudo means we have two stages. So on the real and synthetic data, the real part is the like the A, like this is a red self initial observation. You can see the ego vehicle observation based on the planning. So from the red to the green, this is a stage one real trajectory, okay? And the stage two is a pre-generated synthetic part. So you can imagine there are lots of possible observations based on planning, right? So in this example, we list the three trajectories, which lists as a B, C, D. You can also set up this hyperparameter as 10 or 100. So given this example, we have the purple one. Purple one means synthetic observations is pre-generated with the method called MTGS in the second piece of work I presented earlier, or other 3D Gaussian splatting work. So the combined score, this score is what we call the PDM score to evaluate any end-to-end algorithm performance. So the score is combined or multiplied by the green real one with the different weights. So different weights here is the green one is a true vehicle, right? So the nearer you close to the true distance, the larger weight you're gonna get. So in this example, so you can see three purple B, C, D, right? So in this example, the D part, this generated synthetic one, got the closest distance with a green one. So it's got a larger weight combined with the score that's generated by the trajectories from the algorithm. So this is a score that we called the PDM score, and it inherits all the good merits from both the closed loop and also the closed loop for sure. And also recently, we hosted this Navsim V2 end-to-end challenge. It's hosted at SCCV in this October. This is a poster. I really want you guys to have a focus on the details, or maybe the participants, maybe the leaderboard is online pretty soon, and to keep an eye on the latest development in this field. Okay, the last part, I still got 5 minutes. Okay, so the key challenges, I mean, here I want to list out just one challenges. Is about the RL reinforcement learning, because I really think the end-to-end realm deals with the large scale of data, right? You can leverage unlabeled data and pile up all the large scale data to learn more, like drive like a human without resorting to many intermediate like perception or the other intermediate modules, right? So here, this part, how many RL training iterations are we needed for a robust end-to-end auto driving? You can say call it L4 or L5, whatever the engineering people or the industry will define. So here, recently we saw a very good work. I believe it's from the Valadan group. It's called the Robotic Autonomy Emerges from Self-Pay, also published recently. So the issue is the RL training in simulation is about nearly 2 billion kilometers. That's an analogy from the distance from the sun to the Saturn. It's even very far away. So if you can traverse all the distances in this universe, in this Earth, sorry, so we cannot resolve the autonomous driving problem given the conclusions here, right? So, but it got very promising results. I mean, finally, eventually, it will results and zero shot on real world data sets with nearly zero collisions. That's the very good part of the reinforcement learning. But in the beginning iterations, it got the sample efficiency problem, right? Literally every RL algorithm has it. So the very not ideally part is it assumes perfect perception. I mean, in this work, because it starts from the trajectory input part. And also it's a simulate scene representation and needs too many examples, right? So the question boils down to, do we need to train nearly 2 billion kilometers for a robust end-to-end policy? And here we want to argue that no, it's really not. And corner case example, if we do a very quick calculation, one case, we nearly need more than 200 miles sampling for the robust Tesla FSD, for example. And also it deals with dense reward learning in pseudo simulation. It has to learn from multiple parallel futures. This also may lead to the computational concern for those work. So the future work as to the algorithm engine, which I didn't cover at all in this talk, it deals with how to scale up the RL algorithm to have this dense reward to improve the end-to-end algorithm. Altogether makes up the whole storyline of the word engine. So given the talk at the end, I may have some takeaways. So the first is end-to-end auto driving has made great efforts over the years. Word engine is the next generation for the end-to-end auto driving. But in this talk, I really have this give this very high-level concept. I believe more works are coming in the second half of this year. And also the Nexus is deal with the controllability and reactivity to guarantee both the good parts to generate the corner cases on scene behavior level. And also we propose this MTGS, which consists of the data engine part to ensure multi-traversal realism in large space. And altogether, these two data engine consists of data engine to generate challenging cases for the dangerous scenarios, for example. And the last takeaway is scalability emerges from efficient sampling. For example, the dense reward design in the RL to make it scalable from the data engine. So I'm really happy to have all the teams. Thanks for them. Many of the work comes from my students, and also Chonghao will be the author of Centaur will be at CVPR on site. So we are happy to take any questions. So this is the end of the talk. Thank you.
Okay, thank you. I hope you can hear me. On my side, everything looks good. First of all, I need to say sorry that I'm not there in person. Unfortunately, I was a little bit too much travel, but I'm hope that I can give an interesting talk to you and share some insights and thoughts that I have about self-driving cars and mobile robots and how we can finally arrive at robust learning-based approaches in that context. So my talk is a little bit about the history of self-driving and what is actually needed in order with self-driving cars from my perspective. Second, and what I see is that we have basically seen three major trends in the past maybe 20 years, which is, or maybe even longer, which started with this probabilistic robotics hype, where basically was about state estimation and uncertainty estimation to build robust systems. Then we encountered the deep networks that helped us with the semantics and perception and also in prediction. And then recently there was this trend of the transformer architectures and foundation models, generative AI, which basically helped us to generalize and transfer across modalities and get us closer to that, what we call embodied robots or embodied systems. And that's something that I want to cover at the very end, basically this question of how we can utilize these foundation models in a better fashion to build more robust systems. But the first part will be about this combination of probabilistic and deep network-based approaches and how we can properly do this in order to build to get the maximum or the best out of both worlds. So when you look at probabilistic robotics, then this is just an equation that describes a state estimation and utility optimization. Then that's what we actually need is probabilities, basically these terms over here. And probabilistic robotics has been enormously successful when it comes to robot navigation and also autonomous cars. It was basically the starting point for self-driving cars. And this is something that has revolutionized robotics and also initiated partly the self-driving car domain and space. So the reason for this is that with these approaches, you can get enormously accurate, even in dynamic environments. Right, here's an example of an experiment that we did a few years ago, where we basically could demonstrate that the localization accuracy, even when you cover like the majority of the perceptual field of the LiDAR that this robot is equipped with, then the accuracy lies in the range of millimeters and like way below 1 degree, which basically means that we do have accurate pose estimates. And this is an enabler for navigation and factory floors, but also self-driving cars, because some of the tasks simply become easier, right? What you need to solve there is basically stay on the road, don't get hit and don't hit anything. And the first of those is actually basically relatively easy when you know exactly where the vehicle is. When you look at the software stack of a self-driving car, then typically such a stack looks like this over here. We start with the sensors, and we have this kind of like interpretation module where we do something with the sensor data, and then we feed them into mapping and localization components, generate a map, which we then use for localization. And then based on this, we typically perform prediction, then planning, control, and there it goes to the actuators and the car drives. And from my perspective, where probabilistic robotics is particularly strong at is this mapping and localization part. Partly also prediction, but I think there's a way more or way better techniques out there right now, for example, from the space of deep learning. So this is where we are basically strong and what has basically enabled the navigation component and the localization component of self-driving vehicles. Right, and this has also led to applications in the mapping space. And here is one example of a startup that I created together with some of my students a few years ago. We are basically trying to build highly accurate indoor-outdoor models of real estate buildings, but this can also be parking garage. If you think about a valet parking application, then this is something that would be super useful for a valet parking case where the vehicle can actually localize itself autonomously in a parking structure. And so this is basically something that we are able to do these days and what is a basis for many self-driving car stacks out there. And here you see the most accurate 3D model of the Freiburg Cathedral. And you can also see the indoor structures partly that are underneath the earth. But like when we have a closer look at this question of like what is actually the advantage of self-driving of maps for self-driving cars, then we can see that they are super useful for perception because they sometimes help us identifying objects, or for example, it comes to traffic lights and you exactly know where the vehicle is and where the traffic light is, then detecting the status of the traffic light becomes much easier rather when you don't have this information, right? Also, when it comes to tracking, localization, prediction, planning, control. So these maps have numerous applications in the self-driving car space. However, right, usually these maps are extremely difficult to acquire, right? This is more or less a 3D representation. So this geometry, the geometry is typically easy. It gets a little bit more complicated when when we are getting to semantics. And this is an example in the lower left, right, where we basically have an intersection with traffic lights. And one of the key tasks for a vehicle there is typically to figure out as to whether or what the outward going or the inward going lane is at the end of the intersection, right? So how all these lanes connect. When there's a straight connection, and it's maybe easier, but if you have to do a left turn, then it's not necessarily the case that there's a unique case where you need to actually go at the end of the intersection. So this is a severe problem, and this is typically done nowadays still by so-called map operations teams, and many self-driving car companies have super expensive and large map operations teams that do nothing else but basically defining, for example, the topology of the road network in order to perform the navigation task for the vehicle and the planning. Right. There's other maps, and this is one on the right-hand side that I took from a Waymo page. I don't know what this is useful for, but I can only make a guess. And my guess is that this is a ground plane or the ground point representation, basically all the points that correspond to the ground. And when you subtract these points from your current LiDAR scan, then all of a sudden all your objects are isolated and things become much easier when it comes to object detection and object identification, for example. So this is what is all needed in order to build a self-driving car. And as I tried to explain before, this can be extremely expensive. So, but on the other hand, these maps also pose challenges because they're mostly static. And whenever we are in an environment that is dynamic, like the real life, right, then we often encounter situations like this one over here in typical road in Ann Arbor in the winter, where most of the lane markings are basically not visible simply because of the mud that is the snow that is on the road and the water. So the assumption of the availability of the features that are contained in the map are not always given, right? And that in turn then introduces this requirement of performing change detection, or performing domain adaptation, and so on. And again, updating those is very, very important. And at the same time, it makes the systems very, very sensitive to basically changes. So here's an example where someone put cones on the lane markings on a 2-lane road, at least in the direction of travel here for the Waymo car. And it turned out that in this case, the car actually got stuck on the road, and roadside assistants need to come up and basically rescue the car out of that situation. So it means that minor changes of these maps might result in complete failures of the vehicles, and this is an enormous problem. And this, so basically meaning that we need to have way more autonomy than we currently have. So relying on, or let's put it that way, whereas these maps are an enabler for self-driving cars, at the same time they're reducing the flexibility of these vehicles, and also in the end a level 5 barrier, basically meaning that we cannot drive everywhere. We can only drive there where we have these maps available. And the key question is, from my perspective, how can we do this without maps? How can we get rid of the mapping process? And one way, like one step towards this, is definitely the deep network approach. Right? So how can we utilize deep networks to increase the detection performance of these vehicles and the perception capabilities, and then in the end combine this with probabilistic approaches? This is, from my perspective, the key challenge here. And we all know that one of the typical tasks in perception is this deep learning. In perception is semantic segmentation. We are basically trying to assign semantics to the images that we get. And there's different variants of this, and the one that I'm going to focus about later on is panoptic segmentation. But I think the strength of the deep learning approaches are right now, in particular in this interpretation part, where we're trying to make sense out of the sensor data and assign semantics to the sensor data. And but this is not cast in stone. I'm happy to discuss this, but I think when you look at this, the one before, then this actually calls for this idea of combining the two and getting the best of both worlds, which is actually happening right now. But there's one thing missing, and that's what I'm going to talk about in the next few seconds. Right. So let's start with the idea that we basically take these deep networks and try to develop or to perform inferences based on these networks about what is it that the vehicle sees in the world, right? And what is the semantics and what is out there. And one task that I'm going to focus on is like the extension of semantic segmentation by instance segmentation, which leads us to that what we typically call panoptic segmentation. And of course, we could now try to, and this is what we see in science, that people start to basically train these networks and optimize them on existing data sets and to get performant there. But the problem now is, like, how can we define this with the downstream tasks, which are potentially, at least for the time being, probabilistic based, right? And there we need, for example, these two terms, like the world model and the perception model, right? Basically this question, what is the likelihood of that observation or that interpretation given the status of the vehicle? And this is something that, at least from my perspective, like, should be looked into a little bit deeper. And I will show you like 2 examples of what we have done in this regime and how we basically were able to combine this with this 2 downstream tasks, or with this downstream task localization in a proper fashion and without like manual adjustments of these likelihood terms. So the idea here is to basically have that what we call uncertainty-aware panoptic segmentation, where we not only get the semantic segmentation, but also, or the segmentation, but also the uncertainties. And on the left-hand side, you see this for the example of semantic segmentation with the approach that I'm going to describe in a few seconds. But at the same time, you not only get the individual classes, you also get the class uncertainties, and can do the very same with the instances, the way we basically have instance segmentation and then instance uncertainties. And if we combine the two, then we get that what we call panoptic segmentation. And then here you can nicely see that in particular at the borders of classes and instances, there's a high uncertainty, which is natural from a perception point of view, because there it's extremely hard to identify to which class / object this individual pixel actually belongs. Right, and this is the approach that we are basically, after a backbone, have a segmentation head where we get the segmentations and their uncertainties. and then an instance segmentation head where we get bounding boxes, classes, and uncertainties as well. Then we perform a fusion on the right-hand side, which leads us to these the panoptic segmentation and the corresponding uncertainties. Right, and at that time we evaluated these three metrics over here, where the second one directly follows from the UECE. And on those two metrics, if we look at the statistics down here, our approach outperformed at that time the state of the art, and which is great. Right? So what they get from there is basically an approach that not only provides us with the segmentation results, but additionally with the uncertainties. And it turns out that in some cases, these approaches utilizing both or producing both actually also get more robust in general. And here are a few qualitative results on a video stream. The next was, or let me skip that. The next was that we looked into as whether we can do the very same with also LiDAR. And here we generated an approach for LiDAR panoptic segmentation. And here again, it's just like a teaser image where we basically show the LiDAR semantic segmentation and the corresponding uncertainties. Like greenish means higher uncertainty here, and we observe the very same as before. Like they were at the class boundaries, we are basically we're getting higher uncertainties. And this is the approach. In the interest of time, I will not really go through this, but it basically performs based on the LiDAR input and the bird's eye view projection, like the semantic uncertainties and the semantic segmentation, and then combines them in the very end to get the panoptic prediction and the panoptic uncertainties. And here you can see this again, like with the errors projected as well. So here is the panoptic uncertainties, and this is the error map. And the fact that we see some sort of a correlation here between the uncertainties and the errors, that means that the uncertainties actually make sense. Right? Which brings us to this question of, here's again the video showing this in action on a data set we evaluated the system on. Which brings us to this question, how can we actually combine this, right? And so just producing uncertainties actually is not enough. What we typically need is we need them being calibrated in a way that they can directly be used in a downstream task like localization or mapping. This is what we did in this UPLAM paper, where we basically developed a robust panoptic localization and mapping approach, leveraging these perception uncertainties that we generated before. Turns out that, in fact, they are not calibrated enough. So we needed to add a regularization term to actually convert these generated uncertainties into the ones that can be utilized properly in the localization approach. And here's the basic idea, that we are basically taking the segmentations, uncertainties, and the LiDAR point cloud, perform a BAV projection, and aggregate them in a panoptic map with corresponding map uncertainties, which then at like evaluation time or localization time is, so this is the map generation process. And when we basically test this vehicle in the localization process, we perform this, we calculate the uncertainty aware particle weights, and then use this in a particle filter to estimate the vehicle pose. Again, I will skip over the details of the architecture, but in principle, that's what I already mentioned before. So what you can see here now is the evaluation of this, like truly like this bluish cloud here, or point cloud over here, is basically the particle filter trying to track the vehicle based on this panoptic segmentation, and the uncertainties, given the map plus the corresponding uncertainties as well. And whenever these point cloud stretches out, that means that we don't have a lot of vertical features that allow us a proper longitudinal estimate of the vehicle on the road. So what we rather have here is then an uncertainty in the direction of travel when we don't observe vertical structures like light poles or traffic lights. This is so this is like an important step from my point of view, because we now, with this regularization, we can directly use the outputs of the deep network approaches into downstream tasks for like mapping and localization. And that again brings me to this question, like, do we really need maps? That's something that I really would like to understand a little bit more in the future. This question of are there representations that are not geometric? We roboticists, we tend to always go from sensor data to geometry because geometry is so much easier for us, and it's typically that where we feel home. In geometry, we can do localization, we can do path planning, we can solve all kinds of tasks. And this is something that we have been working on in the past as well. And I think there's a lot of more to go. Like basically, that if we don't need maps, right, then we can get rid of these map operations teams and basically make the self-driving car development much more effective. And so one task, for example, could be this learning of the topology from bird's eye view sensor data, where from looking at like a look at a bird's eye view image, or it could even be a satellite image, trying to infer the topology and of the road network, which is particularly relevant in the context or in the case of intersections. This is an approach that we developed a few years ago. Basically, we call this lane graph net. We have an improved version of this as well. We're basically trying to get from individual modalities and these layers, bird's eye view representation directly to lane graphs, where we get the individual directions of the road network associated as well. Here's a few examples. It's not 100% perfect, and there's probably nowadays better approaches out there, but what I truly believe is that this is an important step to maybe solve these problems and making these tasks way more easy for the human user, and reducing the load of these map operations teams, for example. But then with these upcoming of these foundation models, that has changed somewhat the landscape from my perspective, because we are getting now closer to that what we call embodiment, and the ability to perform cross-modal inference, and basically also using language for navigation as well. And I will give you a few examples at the end of my talk, and would like to stimulate a discussion there as well in this context of how we can, or in the question of how we can utilize foundation models better for automated driving. For me, we are right now at a turning point where, this is why I show this robot ringing an alert bell, because I truly think that with these foundation models, we are entering a new area in robotics, and getting closer to that, what we call embodied robots. And there's two ways of doing this. Like, one is using existing foundation models, and the second one is actually calculating a foundation model. Self-driving car foundation model, for example, would be something that might be super useful for the development of cars. Here's a few examples of work that we recently did. This is visual language maps for robot navigation. It's a work where we are basically trying to navigate with the robot, or instruct the robot to perform navigation tasks based on language instructions, and this in a zero-shot fashion. This is what these models typically allow you to do. And here, for example, the robot has no classifier for keyboards whatsoever. You can simply interact with the robot in a way that has not been possible before, at least not without training the robot on huge data sets. And you can also talk about chairs, or instruct it about chairs, and in a few seconds you will also see a plant in the background. You can tell the robot to go to the plant, and the system is then able to execute this task. Still, here is a 3D representation, or a 3D voxel grid in the background that actually stores the embeddings. You can also do this in a hierarchical fashion, which allows you to provide you, or allows you to give way more complex instructions and to the robot, and have kind of like an open vocabulary system where you can instruct the robot, for example, to find a specific poster, or go to the coffee machine, or whatsoever. And this is something that is super useful in the context of robotics. I also believe that there's definitely an application in the self-driving car space, for example, when it comes to modeling behavior of other drivers, or the behavior of, or the different scenes or edge cases the definition of edge cases or the generation of edge cases would be extremely useful to have such systems attached to, for example, simulation tools. And yeah, so here we also did some experiments for where we actually used these foundation models for vision-based localization. And we found that they are in particular useful when these images or the query image and the reference images are very different in terms of illumination and also viewpoints, right? So there might be zero overlaps in when it comes to the individual pixels of an image, simply because of the transfer through the language component. You can actually get into a situation where the localization becomes way more robust. And here is one example, and that what you see here, this greenish thing in the corner is we call this living art portrait. It's based on moss to actually make the air a little bit better, and that plays a role in our evaluations as well. So here is this question of that what we were able to do with this approach was basically to try to learn which objects are relevant for performing a navigation task. And so what we did is we basically told the system to not focus on that what is called a living wall portrait in the navigation task. And we've realized that when we do this, the localization performance drops dramatically and goes down maximally compared to all other objects that we could actually remove from this data, which basically means that you now arrive in a situation where you can instruct a system to focus on certain aspects in the navigation task. And this is something that is pretty interesting, because then it will allow you to basically tell a system to look for specific parts of specific aspects in order to robustify a task like localization. And here's another example. It's a completely different domain, but also shows the power of these systems for example, collision avoidance here. But this is just like a robot vacuum cleaner. And so there might be things that the robot should actually avoid and not go or run over. And there might be things that it should go over. And this is basically also something that the self-driving car needs to decide. And what we did here is we trained a small network based on the training data coming from a vision language model. And in order to actually learn a policy for these navigation tasks. And the interest of time, I will only quickly go over this. The interesting part here is that we were actually able with this distillation process arrive at a system that shows a similar performance than a cumulative learning approach, and at the same time uses the energy of a naive fine-tuning approach that does performs a warm start from the existing data, right? So you're basically getting the best of those two worlds here and having like a highly performant system that uses very, very little energy. And this is also particularly relevant for self-driving cars, because there you actually probably need fewer compute resources than we right now have in order to make this all financially feasible. And just to give you show you a few examples here. So this is all zero shot. This is not a real vacuum cleaner. So we removed the brushes. And for that, because of that, we don't need to reset the experiments. But what you can see here is that the system, without any pre-training, right, is able to avoid these objects on the ground that it should not suck up. And it's kind of like an interesting, very, very interesting setting for robots and cars encountering situations that they have never seen before. Which brings me to the end of this this talk. Basically, this question, like, is there a way to calculate a robotics or self-driving car foundation model? We have seen this with the OpenMX embodiment paper, right? It took a huge effort to calculate such a model, and a lot of training data collected by people. I think in the self-driving car space, that should be way easier, because we have a lot of data that we can more or less automatically generate with dash cams and so on and so forth. So calculating a open self-driving car foundation model is, from my perspective, a really promising approach to get closer to more sophisticated robots and cars that are more intelligent than the ones that we have, that very, very often still rely on pre-trained data and geometry. Yeah, this is a paper that published by colleagues recently, where the spider web representation basically shows that we are not yet arrived at the there where we would like to be. But I think from my perspective, this is a very, very promising approach for the future, looking into this question of how can we actually learn a foundation model for robotics and self-driving. Right. So what it requires from my perspective for the future is probabilistic robotics still. I'm happy to not needing it anymore. I think deep learning will not go away and will be also a key component in the future. And if you combine the two, we need calibrated uncertainties. From my perspective, more research needs to look into this. And then finally, also this question of how we can train and build our own foundation models for solving these navigation tasks. And with that, I'm done, and I hope you enjoyed the talk, and I'm happy to get your questions.
Okay, so today I want to talk a little bit about generative models for 3D data. And in particular, since we're at the AV workshop, we're going to talk about LiDAR data. And especially, how can we repurpose already trained image models to generate also these very different 3D data? So first of all, like why bother, right? So we come a little bit more from the neural simulator side, right? So we want to be able to simulate scenes, to simulate images like multi-view cameras, and also LiDAR in like what you would have in an AV stack, so that you can actually test your end-to-end models and see how they perform in this simulation. And of course, like NERF or 3D Gaussian splats are good, but they require like per scene optimization. This is usually slow, and they don't really generalize. And generative models are really, like, they're really cool, right? I mean, we see them everywhere. We're generating images, we're generating videos, but they only work for these two modalities, right? Like, we haven't really seen generation of LiDAR data at scale. And LiDAR is important for safety critical AV. And so in this talk, I'm going to focus mostly on certain research questions, like the first of all, can we actually learn the distribution of this LiDAR data? Can our generative models generate this type of data? Can the video priors that we help in our image models, in our video models, help with LiDAR generation? And finally, kind of the holy grail, right? What we want to do is we want to jointly model RGB images and LiDAR data. So let's see how to do that. So I'm gonna start with the NVIDIA Cosmos Foundation model. So some of you might know that it was released a few months ago. It's basically like this video generative model, and it has been customized for physical AI setups, and we know it works well for AV. I will show some images later. And it has like two ingredients, which I'm going to focus on because these are the ingredients that we're going to need to change in order to generate also LiDAR. So the idea would be to repurpose this model. Of course, like the first thing that we're looking at is the video tokenizer, right? I mean, we have completely different modalities, so we're going to have to change our video tokenizer into a LiDAR tokenizer. And then we have the DAT-based diffusion model, which is depicted in green. And I'm going to basically explain like how do we put our prompts, how do we put our conditions in order to generate data that, for example, follow the information of a map or the information of the RGB image. Okay, so we already know that this foundation model can generate AV data, right? So here we input, for example, LiDAR and HD map. So the HD map is the second image. It's kind of represented by different colors. Like, for example, the lane lines are one color, the bounding boxes for the cars are another color. And then we have the caption at the bottom. And this is the generated output that we actually have. And this is already like embedded in this model, right? So this model knows already AV data. So this is already a good starting point. It can already generate multiple views. So for example, here we see the same scene that we want to generate in New York. And in the bottom, in this kind of like sakura, so you see like all these flowers that are falling. And you can see that the views are actually pretty consistent, right? So this is already something that the model can do. So it's a pretty good starting point for AV. And so the question is, okay, let's do enough for LiDAR, right? I mean, the starting point is good, the domain is there, but we need to think about some things. Like the first one is the representation. What kind of representation are we going to use for LiDAR data? Where's the tokenizer for LiDAR? Do we need to retrain it? Can we reuse the video tokenizer? What are the conditions that we can use for LiDAR generator? Can we, for example, generate from map information, from RGB, and how to jointly model LiDAR and RGB? So, okay, let's talk about the representation. So we have like pretty different representations if we think about repurposing an image or video model, and we think about LiDAR, which is basically like a non-structured point cloud. There's obviously like too much of a difference in there. And so what we do is we follow a more structured representation. So we convert LiDAR into range map so that we can basically effectively reuse all the infra that we built for image generation, right? So this is just a question of how to make things easier for us so that we don't need to retrain everything from scratch. Now let's go to the tokenizer. So the first thing that we tried was, of course, like, let's just try the image tokenizer, applied it to LiDAR range. And basically here, like we have the input, and in blue we have the reconstruction, and you see that it's pretty bad, to be honest. So this was our starting point, right? We say without retraining anything, this is what we obtain. It's very noisy. It sometimes doesn't even follow the structure of the road. So the question is, how can we improve on this initial result? Now, there's several things that one needs to do to get a good tokenizer for LiDAR data, and I'm just going to mention 3 aspects. So first of all, you kind of have to understand what a tokenizer is about, right? So a tokenizer is about compression. So you have to be smart about the redundancy of your data. So if you look at the range maps, there are these kind of long image representations. So you have a lot of dense information in the columns, but the rows are something that you cannot really compress, right? So what we did was we basically applied a 4 row repeat. So we stack the range images one on top of the other. And this changes things a lot, right? Because now you're not compressing the raw information so much. And so you're keeping more of the structure of the LiDAR data. You also need to accurately model your sensor, right? So you need to understand your sensor. You need to handle, for example, motion compensation. So you see here how we were training things in the top image, where you see the same structure, which is in completely different positions in the range map. And when you undo motion compensation, then you get the aligned structure. So this is something that you need to take care of, and you need to know how your sensor behaves. And then another thing is model precision really matters for depth estimation, right? So the tokenizer that was used for images used BF16. And if you look here at the map of the depth, you can see that we have up to 5 centimeter inaccuracies just by using that precision. So this is something that we could not live with. So we had to use FP32 to fine-tune the tokenizer while still keeping the diffusion model at BF16. So these are just like 3 ingredients, which are it's kind of technical. It's kind of like these small decisions, but they do make a huge difference. So this is how now the tokenizer looks like, right? I mean, we're just trying to reconstruct the data here, and you see the huge difference that we had from before, right? So now the structures are much more precise, like even the road is straight. The cars are also much better depicted. There's much less noise in general. And this just comes from these 3 changes that I've mentioned. Okay, so let's see what we can do with that. Let's have some fun with that. So the first thing that we can do is try to condition our generation, right? I mean, in the end, we want to generate scenes that we're interested in. And one of the conditions that we can use is using basically HDMap and bounding boxes. So with this, you're basically fixing all the layout of the scene, right? You're saying how the cars are going to move around you. You're saying how the road is going to look like. And then you can change things like, the weather or the buildings, things like this. And we're going to create basically the same representation that we have for LiDAR. We're going to create the same representation for HD maps. So you see here like all the bounding boxes flying around. You see the lanes being marked, traffic signs, things like this. Another thing that we can use as condition is, of course, caption, right? And this is very useful to change weather conditions. So here you can model a rainy day LiDAR, and at the bottom you can model it on a normal day. And you can see really the effects of the rainy day where you just are dropping rays everywhere, right? A classic characteristic of rainy sequences. So, okay, how do we actually control HD map generation? So we're going to have, so this is going to be like single LiDAR frame generation, and it's going to be applied later to the LiDAR sequence generation, and it's going to be exactly the same, basically, for image and for video. And what we're going to do is we're going to input into our DAT diffusion model, we're going to input our noisy LiDAR tokens that then we're gonna denoise. And when we're going to input, we're going to basically concatenate clean input condition tokens, in our case, HD map, right? So the noisy ones are the LiDAR. This is the ones that we're going to denoise. And in the HD map are clean tokens. And so these are the kind of things that we can generate. So here we have at the top the reference LiDAR, the generated LiDAR, and the condition that we have. And you can see that it's not super easy to see, but some of the objects that are being placed in this condition are actually placed appropriately in the LiDAR map. And also the road structure is the same. So here I'm always showing in blue the generated LiDAR and in yellow the reference, but here we're not doing reconstruction, right? So I just show the reference so that you can see the quality of the LiDAR, and you can kind of compare if this quality makes sense with respect to the generated output that we have. Here's another example where we can see two pedestrians. So I think this is really cool, right? It's a scene full of pedestrians. And you can see the pedestrians that are being nicely generated here, even with, shadows and stuff like this. So I think the detail that we get with these generations is actually pretty awesome. Now the weather control, right? I said that we wanted to do weather control. So here what we're going to have is we're going to have the HD map condition, and we're going to have the caption, which is going to control whether we generate a sunny sequence, which is what we get on the right, or a rainy sequence, which is what we get on the left. And again, here we can see like all the rays dropped in the rainy sequences, which is a typical effect that we have for LiDAR data. Yeah, another sequence with another image. So this is, again, single LiDAR generation. And now we go into the video model, right? So the video model is a little bit more complex, but essentially you're going to condition the thing in the exact same way. And you can see here the condition that you have, right? Like you have all the road structure, we have the cars. And this is the kind of sequences that we started generating. So you can see that it really follows the structure. It really follows the objects. It's a little bit more noisy than the image model. And now let's go into what we actually want to do, right? I mean, we want to model the full stack, right? I mean, we want to model the LiDAR as well as the RGB, and we want this to be paired, right? We want the information to be paired between what we're looking in the multi-view cameras and what we're looking in the LiDAR space. And so how we're going to do this is essentially we're going to have our noisy LiDAR tokens, which are infused into the diffusion model, which are going to be denoised. We're going to have the noisy image tokens, which are going to be denoised. And we're going to have our HD map condition, same as before. This is clean. This is not noised. And we're going to have some view embeddings, right? Because you want to be able to tell the model to generate different views, and you want to be able to encode these different views. So you can think about this as, you have one view, which is the LiDAR, and all the other views are the images. You can also think about it this way. And we have one model for both. So this is important, right? We don't have a diffusion model for LiDAR and a diffusion model for RGB, but we have a single model for both. And now we can see the kind of things that we can generate, right? Like this is the reference image, this is the generated image, and the condition with all the road structure and the bounding boxes. And one thing that we wanted to check, right, was how does it align, right? Like how does LiDAR align with RGB? We want to be able to show that we have the same structure in the same 3D position. Otherwise, any model that you train is not going to be accurate, right? Because it's not going to have the right information at the start. So here what we do is we basically project the LiDAR into the images, and we see that it follows the structures pretty nicely. So this is the generated output, and we see this is a straight road. It's generating the straight road. There are some cars also parked, which are also being generated. And here's another projection where we have a bridge. So this is pretty cool because there are not many bridges in the data. But still it's able to capture the structure of the bridge, and you can also see the LiDAR points here that are being correctly projected on the bridge. And also you can see the structure here in the LiDAR data. So that's also pretty cool that we can generate data that we haven't seen so many examples of. What happens if we want to do a different thing? We want to, instead of condition on the HD map, we want to condition on the RGB images, right? So we have plenty of stacks that just have multi-view images and they don't have LiDAR. What if we actually want to enrich those stacks with LiDAR so that then we can train, we can measure for, safety measures, explainability, things like that. And so this is also something we can do, right? In that sense, you don't put as a clean input the HD map, but you put your image as a clean input and your LiDAR as a noisy input. And then you just denoise the LiDAR part. And this is what you get. Also like very, very good alignment between RGB and LiDAR images. So this is basically an RGB image to LiDAR, 6-camera model. So we get like the 6 cameras as input and we generate the LiDAR as output. And we see like all the cars are correctly generated in the LiDAR space. The alignment is actually pretty good across all the cameras, and the 3D structure also looks really nice. Okay, so just for some final thoughts. So we started with the results of this tokenizer, which were actually quite bad. By putting some effort into understanding the sensor, understanding the noise in the data, understanding what a tokenizer actually does and what information we want compressed and what information we don't want compressed, we could get to a nice generative model that generates much more crisp LiDAR, where we can observe cars like very nicely. We can observe like even pedestrians, like thin structures are properly generated. And this was done by post-training the Cosmos-based model for LiDAR generation. So all the nice video properties and priors that the model has are built into the LiDAR model. And there's actually pretty decent alignment between the two modalities. I think this is something that we can improve on. But basically the main objects, the main structures are really nicely aligned. And so, yeah, with this, I will open the floor for questions, and thank you for your attention.
Okay, thank you very much. So I'll be speaking about some efforts in our lab on perception and simulation in the context of self-driving. So building upon what Laura discussed at length. So I think one super interesting starting point is the fact that there's some version of simulators that are actually available now for people to use. And perhaps the first instantiation of this was New Plans. So this notion of actually taking pre-recorded data sets and turning it into a live interactive simulator that you could run a planner on and evaluate. And so this I thought was a fairly recent but very sensible way to think about it. And of course, since New Plan, there's been other efforts from Waymo as well. So what I wanted to talk about, three specific pieces of work that we've done in the context of this. The first was our own entry into New Plans, and then some sort of lessons learned from that space. Okay, so first I wanted to sort of dig into what does it take to turn a recorded data set into a simulator. And importantly, when we say simulator here, one thing that's different than what Laura talked about is that this is not really a sensor simulator. Maybe I would call this more like a behavioral simulator. It operates at the level of objects and tracks. But nonetheless, this is still useful for, let's say, focusing a bit more on the behavioral aspect of how do things move and react with regards to one another. It seems like the sensor simulation part, there's been a lot of impressive success on looking at some of the work that Laura pointed at. Okay, so first, one of the starting points for thinking about how to take recorded data and turn it into a simulator is how do we evaluate this? And the first place I've seen this laid out was in the New Plans Challenge. So I just wanted to talk about this. There are three specific ways of, if you have a recorded log with the ego vehicle moving around in an interactive world, to think about how to evaluate a new plan for the ego vehicle. The easiest way is the ego vehicle actually went some trajectory in the future. Let's say this red path, and you can look at the plan for the ego vehicle that is given by a planner that's actually being evaluated in this simulator, and you can look at the difference between where the planner thinks the ego vehicle will be in 5 seconds from now and where it actually is, and then look at the deviation. So I might think of this as a forecasting metric, but applied to the ego vehicle. What's much more compelling is, well, you actually let the ego vehicle drift from the recorded path. So if that happens, if the ego vehicle says the plan says to go straight, then it continues going straight. But because everything else is a recorded data set, all the other agents can just play back the way that they move. So one problem with that is you'll see behaviors like this, where the ego vehicle might decide to stop, and then everyone else will just continue to move because that's what they did in the recorded data. And so we'll call this a closed loop ego simulation because the ego vehicle can change, but an open loop agent simulation. And of course, what you really want is a reactive simulator where if you do something out of the ordinary, the rest of the world reacts. And so the New Plans define this as a closed loop agent simulator where the rest of the agents don't just play back what they did, they respond to what the ego vehicle is doing. So another way to think about this is that this simulator should behave like a game. I should be able to joystick control what the ego vehicle is doing, and stuff should react to it. Okay, and the first blush is like, okay, well then how exactly should agents react? And there's various ways to go about this, but it turns out a really simple model for reactive control is a PID controller, a proportional integral derivative controller, which you might remember from your old controls class. But in the context of vehicle dynamics, this is oftentimes called an IDM or intelligent driver model. So this always kind of perplexed me, but I just wanted to hopefully not scare you guys, and that it's actually just about 10 lines of Python code. It's extremely intuitive. There's 5 big parameters that says how close are you willing to get to the lead vehicle, what is your max acceleration, what is your min acceleration, and given all this, you can write some pretty simple logic that basically lets every agent it will let all other vehicles almost behave as if they're on adaptive cruise control. That's one mental model I have. Is that you can have your own adaptive cruise control. It'll follow the path that it was given, but it won't run into something. It'll slow down if it sees something in front of it. So it turns out that kind of reactive logic is pretty straightforward and you can put into these simulators. And what's nice now is that now, if you endow your other agents and recorded data set with this logic, you now have a simulator. It will react to how you're moving. Okay. And I think an interesting way to think about how to, okay, so now I want to think about, that's just a background on what New Plans is, or how to, more generally speaking, turn a data set into a simulator. So now we actually want to evaluate a plan. We want to do some kind of attempt at something end-to-end-ish. that will control what the ego vehicle is doing. And maybe I should be a bit more clear. So we could do something end-to-end-ish, which would be a policy or a reinforcement learning algorithm that's learned that takes some perception state in and returns back acceleration and steering angle. Instead, what we're gonna we decided to follow something a bit more classic, I think more closer to what current deployments I suspect are following, and that is a model predictive control. So here, what happens is that there's the little logic inside of the ego vehicle's head. It maintains an internal world model about how it thinks the world is going to unfold. And it does some rollouts, and then it will optimize for the best path that will get it toward its target waypoint without running into without incurring penalties on the optimization. And so all of this is in some ways a classic control strategy. I just want to point out that even LeCun, I think, advocates for a version of this as his view of a path towards autonomous machine intelligence. Although in the document I couldn't find the term model of predictive control, from my perspective, that is what he's suggesting. But the crucial thing here, though, is that we need a really good model of how the world's going to unfold, and that very naturally plugs into all the contemporary work on world modeling. Okay, so starting point of, okay, so now hopefully we all get a sense of what this benchmark looks like. And when this was released, there was different ways of evaluating. Remember, C1 was the ego forecast, which I'm not really going to follow. C2 is actually the planner can move off the path that was in the recorded data. And C3 is the real setup where the rest of the world can react. And when this data set, or when the benchmarks was released, one sort of frustrating fact was that simple rule-based planners did much better than any learning-based solution. And this was kind of, I think, maybe one of the reasons why. Well, let's see. I still think this is a really nice data set and a really nice simulator. I'd love to hear more comments on this, but I have a feeling that because it was hard for learning-based methods to shine, it didn't get as much traction as it maybe should have. But here's a starting point that we had about how to sort of, starting with those more classical solutions, is there a way to put some learning into it where we can get better with data? And our starting observation was that if you look at these control parameters, actually, let me take a step back. You don't look at these control parameters. You look at actually the real data that was in these logs. And one of the interesting things about New Scenes is that includes different cities. What you find is some of the statistics of how people drive seem to be different. So we can measure, for example, what the typical min gap is for a driver to the next one in front. And we find that in Boston, for example, there tends to be more tailgaters. There's a peak of drivers that will follow closely, that will follow 6 feet behind the lead vehicle as opposed to 10 feet behind the lead vehicle. And so what that got us thinking is maybe if we're going to take a model predictive control approach and we actually have a little world model of how we think the world's going to unfold, maybe the world model should depend on where we're at. Because if we're in Boston, we believe that everyone else is going to drive aggressively. So that's what we should be thinking when we try to optimize for our path. And in another extreme form of this, of the running joke that we always tell is that if you ever drive in Pittsburgh, there's a specific maneuver in Pittsburgh called the Pittsburgh left, which is when if you're taking an unprotected left turn and the light turns green, it's customary that you let the other person that's making a left go first. So this is not an official rule of the road, and if you're not used to it, you will be in for a rude awakening. But it's kind of emphasizing the fact that there's actually culturally dependent factors on how people drive and the behaviors they engage in. So our starting point was that why don't we then try to kind of model these behaviors with essentially inverse optimal control. All of that sounds fancy. All we really did was, given that we know we're going to model all the other agents in Boston with some intelligent driver model, let's tune the parameters, the min gap distance, the max acceleration, min acceleration, so that when we tune the parameters of a controller and we run the controller with those parameters, it looks like the data that we see. So that's all that is. So we just do a grid search and optimize for the best parameters for every city. And what that tells us is that is not without surprise that when you're in Boston, if you really want to simulate the way Boston drivers behave, you should use a smaller theta 3 in your IDM controller. And now you can think about optimizing this for every city. What is the best thetas to use? You can even do this per log or even per agent for each individual agent that you see. Does this happen to be an aggressive driver that likes to tailgate or someone that doesn't have a max acceleration that's very high? So we go through this process of fitting these models, and then we can actually, once we fit these control parameters, then we could just roll out and say, okay, what do the agents look like when we run it with their control parameters? And this is also not surprising that if you fit a control parameter that says you're willing to tailgate, when you roll out potential features, you'll see tailgating. So that suggests that we can almost get a label for these different control parameters and all this data set, but how do we actually use it on test data when we're actually going to go and run a real planner live on robot or in the simulator? And the sort of the insight that we wanted to kind of advocate was we can reuse all the machinery people already use for forecasting trajectories, but instead of forecasting trajectories, what we're actually predicting are these control parameters. So we're trying to predict for every agent, is this an aggressive guy? And the way we're trying to predict that is we're looking at the past history of how people have been driving in the most recent 5 seconds. It's the same history one of these models would use to predict future trajectories. And then once we have these parameters that are predicted, we simply use that in the rollout for model predictive control. So at the end of the day, the final stack looks really classic. It's doing an optimization. It just so happens that the world model has a little bit of learning in it. We just try to learn, does this look like an aggressive driver or a passive driver? And it turns out that's relatively simple to learn by looking at a past recent history of how people are driving. We can do some fun visualizations of these parameters and TSNE plots and group the fits of individual agents by city. We realize, oh yeah, people in Boston do tend to tailgate, but sometimes there's tailgaters in other cities as well. I'll skip this for the moment, and let's sort of get to the final numbers. So now, like, once again, we're just repurposing trajectory prediction models for IDM controlled prediction. And once you do that, we just put it into an MPC controller and you get an improvement, which is we can choose to learn IDM parameters that are specific to each city, or we can even choose to learn ones that are going to be predicted differently for every log. So even if we're in Boston, maybe at a particular sequence, it looks like everyone is being passive as opposed to being aggressive. And what we see is an improvement. And so this is maybe not, at first blush, it looks like it's not that big of an improvement, but just to point out that the max performance here is 100%. So we're actually decreasing the error by a noticeable amount. And what's kind of fun is in this world, you can play these games of what happens if you perfectly knew the control parameters to use for each other agent, if you knew if they were going to be aggressive in the future or passive. And you can show that the predicted control parameters are pretty close to the optimal ones you could fit post hoc. And what's kind of fun is the city oracle is actually not an oracle. It's a completely implementable algorithm. It's akin to saying that when you drive in Boston, you know that you're in Boston and people in Boston tailgate. So you will use that model. It seems totally fair to use a city-specific model if you're so inclined. Okay, so here's some sort of visuals. On the right-hand side is if you do a normal model predictive control with a standard fixed IDM control parameters, and you'll see a collision in frame 21 where the ego vehicle will collide with someone. Down here, you'll see collisions in frame 10 and 23 if you just use a fixed default IDM control parameters. And in our case, of course, we're going to learn how to predict the parameters based upon the city that we're in or based upon the current history of the other agents, and that gives you a little edge. I'll skip this for the moment. Yeah, so I guess so one sort of take-home message from here is really thinking about, instead of putting a lot of machinery into predicting exactly how the world's going to unfold in terms of space-time trajectories, this is saying, well, we believe the world's going to be reactive or agents are going to be reactive. So what we're really trying to do is predict, in some sense, their rewards or their inverse control parameters. And so I think this is one way of actually letting learning shine. And hopefully you can do better at this the more data that you have about learning the behaviors of other agents in your in your world that you're going to enroll. Okay. All right, I'm gonna keep the time here a little longer than I would like. So I wanted to have two more sections of the talk. The second section is, so I think if we kind of zoom back out, in the world of building simulators for helping to address the self-driving problem, I think that while there's enormous work on building better sensor simulators, I think we'll sort of need to address this problem of how do we build better behavioral models. And what this is really about is understanding motion. So there's another sort of track of work we've been involved in that really leans into the problem of how do we understand how things are moving across time from logs. And sometimes this is called the scene flow problem, in particular applied to LiDAR data. And I just want to talk about a few bits of work that we have in this direction that I think have some interesting consequences. Okay. So the starting point for the work I'm going to show is an old paper, not from us, but from another group at CMU called Neural Scene Flow Prior, that talks about a method of if you have two LiDAR frames, how you can automatically compute a flow vector that tells you how everything is moving. So if we zoom back out, if we can do all this kind of motion extraction at scale, then my claim is we can build better behavior predictors. So right now I'm going to zoom back into this problem of how can we at scale learn really exquisite models of how things are moving and changing over time in these log sequences. And so what Neural Scene Flow Prior does, it does a really kind of classic approach at this point. It learns a scene-specific MLP that if you give it an XYZ spatial location, it spits out a flow vector. And the way that it learns is with a chamfer loss. So given all the blue points, we push them through an MLP that will say how they all shift. And then we look at a chamfer distance between all the shifted points and the actual points we see in the next frame. Those are the orange. We get an error signal, and now we can optimize and learn a better MLP. And this is it's almost akin to per frame optimization of a NERF neural rendering model. Okay. So the kind of series of work we have in this direction that kind of builds us up to something that we can learn at scale, something we can learn motion models from at scale, and also with hopefully high accuracy. As the first observation is that this, just like Laura was suggesting, per frame optimization, although it tends to produce good fits, it's really slow and expensive. But a simple kind of almost trivial observation is that, well, you can do all this at train time. Think about then this is a way of producing scene flow labels and just train a super fast feed forward student model that just given a pair of frames, push it through a network and it will spit out a UVW flow for every point. And it turns out you can do this and get pretty good performance, basically a model that's just as fast as the fastest feed forward models, but it's as performant as these per optimization models. And you can do this without ever needing any human labels because you can just use this very expensive per scene optimizer as the teacher. So we had a couple other interesting, for me anyways, I thought this was interesting, works in this direction, which is if we think about ways of building models that can really understand motions in a self-supervised fashion, could we actually use pseudo labels, predictions from an explicit supervised model to self-train on? So the starting point for this is if you look at existing methods for scene flow, what we find is that actually small objects disappear. They're not modeled very well. And this is very concerning if you think about people. They're not modeled at all in any of these motion data sets for scene flow. So we came up with a kind of almost a ridiculous strategy, which is, well, one way of predicting the motion of every point is let's just run an explicit detector and tracker, and that will predict the movements of all these bounding boxes. And let's just project that to the points and see how well does that do with scene flow. How well does that do the scene flow problem? There's this comically titled paper, I can't believe it's not scene flow, that basically outperformed all other methods for scene flow just by solving the supervised problem, just downloading a detector and tracker and estimating how things move. And this really shined for small objects because otherwise they just get swamped when you try to do this self-supervision. Okay. So that was sort of an interesting eye-opening thing that to me, it was interesting because it kind of, even though motion estimation is a low-level problem, this to me kind of challenges the notion of what is high-level perception versus low-level perception. I like this because a true benchmark should just define a task, and maybe we'll discover that high-level cues are better for addressing that task. So maybe the best way to estimate motion is to first explicitly detect and track things, which is what this plot suggests. But there's a recent piece of work that the collaborators Kyle Vetter did, which was a really nice extension that almost went back on this. It went back to the test time optimization, so this is really slow, but it's a really seemingly elegant way to think about long range motion estimation from LiDAR. And let me just sort of dig into it. This is much more like the first neural scene flow prior work that I showed. And the insight that Kyle had was just train a neural scene flow model, or like a deformation nerf, if you will, but instead of training it on a single pair of frames, train it on a long sequence. And so you're training one model that takes as input an XYZ and now a timestamp, and now it will spit out the flow at that space-time location. So at some level, it's a really simple architectural change, but conceptually what's happening is that you're essentially sharing structure between all these per frame models across an entire sequence. And that by itself, just doing that, allows you to learn much more accurate long-range flow models. And we use the term Eulerian flow as opposed to Lagrangian for two reasons. One is, I think this is actually different than the typical way we see motion being modeled for neural reconstruction with nerfs or splats. Usually what happens is you have some canonical frame that represents the structure of the world, and then you learn a deformation model from that canonical frame. And so what you can think about that, like there's this old kind of from the simulation literature, this notion of two different approaches to talking about motion. One is Lagrangian, where it's more particle based. So you actually have a particle in some canonical state, and you track how it moves. There's another way to characterize motion of a fluid, where you just characterize for every point in space how much fluid is moving at that position. So my claim is what we're actually training when we train this deformation field is it's an Eulerian model. You can query it with any point in space, and it returns back the flow, the fluid flow at that space, at that point. And the reason why I call it Eulerian is that you can actually chain a bunch of these things together to get a long-range estimate of flow, which is what those visualizations were. Here, it's essentially doing Euler integration of all these little difference vectors. But this ends up producing a pretty dramatic improvement in the ability to track points over a long time frame. So once again, this was surprising to me because this is essentially not the big data story. This is the per scene optimization story. So the downside of this is painfully slow. So what Kyle's trying to do now is to do the same story of distilling this into a feed forward model that can be run efficiently on vehicle or on car. All right, so I have 5 minutes left. And maybe I'll just briefly advertise something that I think another speaker will talk about next, Nihar. And that is, in this goal of trying to produce accurate simulators where the thing we really want to see is interesting behaviors, there's this sense of we kind of, in order to populate our simulators with interesting and compelling scenarios to really stress test our stacks, we'll have to kind of search for needles in a haystack. The hypothesis that we're making is the first thing we want to do is, given the loads of terabytes of data that we have, we want to find interesting and safety critical scenarios from which to identify behaviors and then populate simulators with those kinds of behaviors. And so this is motivated by, I remember one time when I wore my Argo hat in industry, I remember one current refrain was that, in some sense, it's not enough to build a stack that works. You have to build a stack that is demonstrably can be demonstrated to work. What that means is you have to make a safety case. You have to assemble a really stressful validation set that spans all these different operating domains, weather conditions, scenarios where pedestrians are walking in an occluded fashion behind another car. So our thinking was that this seems to be a really nice place where we can lean into this incredible effort and innovation on vision and language and multimodal processing. So, imagine if you have terabytes and terabytes of data and you want to find a particular sequence of a vehicle making a left turn through an eco-vehicle's path while it is raining. Um, the claim is by assembling large language models and even programmatic instantiations, we can almost build code that can then take off-the-shelf detections and tracks and try to surface these interesting scenarios. So one of the things that Nihar and Kanan did, I'll just give another example of these sort of interesting prompts. An eco vehicle behind another vehicle being crossed by a jaywalking pedestrian. These are all prompts that are motivated from a planning-centric perspective, in the sense that we want to be able to validate and train a planner on this kind of data. So the first thing we want to do is find these needles in a haystack in large data sets. I'll skip the method in which we kind of put this together, but the take-home message is that we tried to formalize this as a scenario mining challenge that Nihar will talk about in a bit, where it's a bit like an integration of, maybe it's almost like an advertisement or an invitation to the huge kind of growing body of work on vision language modeling, to think about the problems of data curation for an AV world, where we query with particular interesting scenarios and we link that to actual code that can surface and retrieve interesting behaviors that we can then use to populate and validate our simulators. I won't go through the ways of measuring accuracy, but maybe I'll then kind of bring it back to the sort of summary. So building off of what Laura was saying, it seems like simulators are going to be an important part of the stack for both training and validating planners. I thought new plans was to me, really nice attempt at trying to formalize the problem of how do you take a recorded data set and turn it into a simulator. And I think there's interesting ways about trying to merge classic autonomy pipelines with data-driven world modeling. The second part of the talk really focused on this. If we really want to model behaviors, getting massively large data sets of how things are moving, is really asking about solving some form of the scene flow problem, and I think there's been some sort of fun innovations in that space. And then lastly, to kind of find interesting behaviors and scenarios, I think we can kind of make an appeal to all of the interesting work on vision language modeling. And I guess I will leave it there. Thanks.
Hi, hey everyone. My name is Ishan. I currently work at Stack AV, and I used to work at Argo AI. So I'm going to take away the presentation for the Argoverse competitions for this year. Okay, so just a quick outline. We're going to talk about what Argoverse is, the current status of it, and then we're going to go over the 3 challenges that we have for this year, which are unsupervised scene flow, which Deva kind of already talked a little bit about, the scenario mining challenge that he also advertised for us, and then multi-agent forecasting. So just really quick to refresh everybody, Argoverse is a collection of 4 datasets that was gathered by the Argo AI autonomous vehicles across 6 US cities. We have the sensor dataset, which consists of LiDAR, camera, HD maps, and 3D cuboid annotations for over 30 classes. We have the LiDAR dataset, which is unsupervised, unlabeled LiDAR point clouds from 20,000 scenarios, with 64 beam LiDARs. And so this is useful for self-supervised training. And then we also have the motion forecasting dataset. This is over 250,000 scenarios, vector maps, and then object tracks for 10 object classes. And then finally, we have the map change dataset, which contains LiDAR imagery as well as vector map data. And this is specifically focused around scenarios where the maps have changed specifically. So yeah, if you want to get involved and use this data for any of your challenges or participate in our challenges, please feel free to check out the Argoverse user guide. We spent some time and effort, Ben specifically, to revamp this in the last year, and hopefully this is a nice API to use the data. And so then just really quickly to kind of touch on, the state of Argoverse, again, after Argo, which has shut down like over 3 years ago at this point, it's a community-led effort. So all of us who are kind of hosting these challenges and participating in them, this is all driven entirely by the community. And we actually were able to launch a new challenge this year called scenario mining. So that's just a testament to how strong the community is and the fact that the dataset is still being supported. And we welcome any ideas or support from you guys. So please feel free to check out the API, submit a pull request, or contact us if you're interested in hosting a challenge or using this data in some way. There's already been kind of various data sets like OpenLane and stuff that repackage the Argo data to be used in other challenges, and that's really inspiring. Also, I'd like to thank Amazon AWS. Their open data set initiative has been hosting Argoverse since its inception, so we're very grateful to them for that. Okay, so quickly to talk about SceneFlow. I think Deva already mentioned about this stuff in his previous talk, so I will try to be brief. But obviously, we care about motion. We want to know about objects are moving and how they're moving, understand the world in that sense. And so, SceneFlow is this kind of per point association of what points are moving, between consecutive frames of a lighter point cloud and how they move. And so, in order to get labels for this, we are using the Argoverse 2 sensor data set, which consists of these 3D object tracks. And so we can, associate the points with the bounding box that they're within, and then apply that motion, to those tracks. So if that looks something like this, we have 2 bounding boxes and 2 different time steps, and then we associate them using the tracks that are provided by ground truth, and use this to get the CFlow labels. I think Dave also mentioned some of the problems that can arise with CFlow, and so I'll talk about how we kind of tailor the evaluation metric to solve these challenges. And so if you're familiar with optical flow, you might be thinking that average endpoint error is a good way to measure the error here, and that was the traditional metric for SceneFlow a long time ago. It's also used in optical flow, but there's a problem with this, which is that average endpoint error is dominated by points that are in the background which don't move at all. And so it actually turns out that like over 80% of the points are background. They're static, they don't move, and so it's very possible to get very good average endpoint error because you're averaging by just ignoring all the moving classes, and so just predicting 0 flows. So you don't want to do that. So in order to resolve this problem, there was a paper here by Chodosh and Deva and some other people, which proposed 3-way endpoint error. And that is a breakdown of all of the points in the point cloud based on whether they're static, dynamic, or in foreground or background. And that allows us to compute a little bit better error. And so this was the predominant metric for the previous CFlow challenges with Argoverse 1. However, even this has problems. Again, Deva kind of like alluded to this and pointed out some examples where it turns out that the foreground classes are still, all the points are dominated by these large vehicles, and pedestrians and other vulnerable road users, they make up less than 1% of the data. And so you can see that it's possible to get very good 3-way endpoint error and still ignore all the pedestrians, and that's really bad. Resolve that. Okay, so here, this is the same thing. We can see that we have a lot of issues. A lot of these state-of-the-art methods have issues with pedestrians and detecting and follow them. Okay, so the metric we came up with to resolve this is called bucket normalized endpoint error. And what we do is we basically take all of the dynamic objects and we bucket them into the classes that we already have from the ground truth labels. And then in addition, we also normalize all of the flows based on their velocity, the average velocity of that class. And normalizing is important because it allows us to compare error between the different classes. So we can know that like error is now a percentage, and we have 20% error on pedestrians versus like 10% error on cars. And that allows the metrics to actually be comparable, because if there were absolute values, cars that move much faster, they would have a higher error, for example. Okay, so that was an overview of the metric, and obviously we used the same metric last year as well for the challenge. So we've had incredible progress in the last 1 year. So here's the state of the leaderboard as of like yesterday when I took the screenshot. So you can see last year's methods are like near the bottom of the leaderboard. So the one, let's see if I have a pointer. Okay, right. So this was the supervised track winner from last year. And you can see that we've already surpassed it with a bunch of other supervised methods. Here was the baseline. This was the method that Deva talked about, where we use the tracks from an object detector. And then down here was the unsupervised challenge winner from last year. And so you can see there was a lot of new entries, and a lot of progress has been made. So with that, let's kind of talk about the supervised winner for this year's challenge, which is Delta Flow. And they have a GitHub repo here, so you can check out their code. So the key insight of Deltaflow is that temporal fusion is very expensive. And so what they propose is using features that are actually a delta of the previous time steps feature instead of concatenating a bunch of brand new features for every time step. So what does that look like? Well, traditionally, in a temporal fusion pipeline, you would have multiple point cloud frames. You would then kind of compute features over those point clouds with like a voxel grid or something. And then you can see here, you might concatenate them together to build one big feature. Or you might do some kind of like 4D temporal convolution thing and then try to build a four-dimensional feature this way. And these things are all very computationally expensive. So either you're going to be expanding the amount of memory you need on your GPU by a lot, and then also increasing the size of the feature tensor, so more computation, or you have to do this like 4D convolution, which is also very expensive. And so what they propose instead is computing these delta features. So they take the feature maps at every time step and they subtract the previous features, and then using the delta time step, the delta scheme, they're able to kind of get one final feature map that's used as input to the model. One other thing that they did in this paper is they also incorporated a category-based balancing loss. And this is really interesting because I remember in last year's challenge, we actually suggested that somebody should do this, and we were surprised when none of the entries had done it. And so, Deltaflow did include this, and it gives a nice 3 to 4% boost on pedestrians and vulnerable road users, which is very nice. The other really cool thing about Deltaflow that they did is they also did cross-domain experiments. So they actually trained the model on Argoverse and then tested it on Waymo and vice versa. They trained it on Waymo and evaluated it on Argoverse. And I guess technically, based on the rules of the challenge, that counts as an unsupervised entry because we said you could use pre-trained models from other data sets. Although I think it was not really in the spirit to use another scene flow data set. We were more hoping for like RGB or other foundation models. But it is a really cool experiment. And so with that, I will then transition into the unsupervised track. So again, this is the state of the leaderboard. It turns out for unsupervised methods, our own Euler flow is actually still state of the art. No one has turned out to beat that. But I instead want to highlight another method that is at CVPR this year, which is just as good. Like it is very close. It is Floxels. And so Floxels has the performance that is like, a few percentage points of Euler flow. It's very close, but it solves the runtime issues that Deva was talking about in his talk when he mentioned it. And so this is really cool because what they do is they apply the trick that has already been applied in NERFs. Right? So we talked about how neural scene flow prior is basically a deformable NERF. And so in NERFs, what's common to speed them up is to just use a voxel grid instead. And so Floxels takes some of the ideas from NERFs and some of the ideas from Euler flow, and instead of using this like MLP neural prior, it uses a voxel grid to optimize instead. And this gives them like incredible speed ups. I mean, it is 100 times faster than Euler flow. It's not real time. It's still kind of in the realm of a test time optimization technique, but it no longer is going to take you like 24 hours to get really good scene flow on a single sequence. So there's some other advantages with this as well because they're doing local optimizations with this voxel grid. There's less background artifacts and better convergence dynamics. So you can see that in this. And then, when it's used for kind of point cloud accumulation, you can see that the background artifacts kind of go away compared to MLP-based methods. And this is really valuable, for getting very clean scene flow and accumulating moving objects in a point cloud over time. All right, so this is really cool. And that's all they have for scene flow. So I'm going to hand it over to Nihar for scenario mining.
Cool. Thanks, Zhan. Okay, so as Deva briefly touched upon, we wanted to explore the problem of scenario mining, and this is broadly motivated by the fact that autonomous vehicles are out there in the wild right now, and they're collecting terabytes of data. And most of the data is not very interesting. So as you might imagine, everything that you see in the wild follows a long tail distribution. So it's really quite a challenge to find the interesting and safety critical scenarios in your sort of treasure trove of data. You need to sort of sift through all this information to find the interesting things to train on and eventually test on. So this was sort of the motivation for this challenge. One sort of thing to note is that this challenge is not really operating in a vacuum. It's very similar to other efforts in the community. So it's very similar to referential multi-object tracking, which, given a natural text query, you want to find the associated object and track it over time. But different from prior instantiations of similar challenges, we're mostly interested in interesting multi-agent interactions. So if you have a whole bunch of agents in a scene, how do they interact with each other, and how does this actually translate to interesting and safety critical behaviors. And just to sort of call out, this is almost the inverse problem of scenario generation. So this is another challenge, which I think the Waymo folks will talk about later this afternoon. So to study this problem, we curated a large-scale data set, which we call RefAV. And this is towards the goal of building planning-centric scenario mining benchmarks. So within this data set, we have interesting scenarios like a passenger vehicle near a stroller on the road, or pedestrians walking between two stopped vehicles. Similarly, we have things like a bicycle passing between a bus and a construction barrier, and then an ego vehicle approaching construction zone with a traffic controller. So these are all sort of interesting multi-agent interactions, which are sort of not obvious on the face of the types of labels that we already have within the Argoverse dataset. So importantly, we had to derive these labels from the existing sensor dataset annotations. So the problem set up here, as I mentioned, is very similar to referential multi-object tracking. So you're given a natural language description, like find the vehicle stopped in front of a jaywalking pedestrian, and you're given rich multimodal sensory inputs, like an HD map. You have a LiDAR point cloud and an RGB image, a set of RGB images. And it's important to note that this is an offline challenge. So you have all the sensor data for the entire log sequence. So you can run your very expensive off-board perception models to really reason about the contents of this log. So the challenge is really parameterized to find interesting scenarios within a 50 meter by 50 meter range. And we're mostly looking at multi-agent interactions between the 26 most frequent categories labeled within the Argoverse 2 dataset. So this sort of gives rise to this problem of spatiotemporal scenario mining. So given an example of a vehicle making a left turn through the ego vehicle's path while it's raining, in green here we have the referred object, so that's the vehicle, also shown in green on the visual there. In blue we have the ego vehicle, so that's related to the prompt. And then in red we show all the other objects in the scene, which are sort of useful to detect, but not necessarily relevant for this particular scenario. So the way in which we go about evaluating models on this benchmark is through tracking-based metrics. So I just want everyone to recall a very popular tracking metric is HOTA, higher order tracking accuracy, which decomposes tracking into its different components. So you have a detection component, an association component, and a localization component. And HOTA basically combines all these together to create a single number that describes how well your tracking model performs. So we tweak this slightly, and our primary metric is HOTA temporal. So it's exactly the same thing as HOTA, but now we only consider scenario relevant objects during the precise timestamps when the scenario occurs. So instead of tracking all cars, now we're just looking for the timestamps when the car is turning left, for example, if that's the prompt. We look at a couple of other retrieval-based metrics. So this is more in the spirit of traditional scenario mining types of metrics. So the first metric we look at is log balanced accuracy. And this is really a log level classification metric. So can your method accurately determine whether at a log level, you can figure out whether or not the scenario actually happens? Similarly, we have an extension to the timestamp level. So we have this timestamp balanced accuracy, which is basically looking at every timestamp, can your model correctly identify whether or not the scenario is actively happening? Okay, so now given all of these metrics and the setup, we propose a sort of interesting baseline which leverages all the recent innovations in large language models. So we propose a two-stream approach where in the first path we have multimodal RGB and LiDAR, which is processed by a sort of slow offline 3D perception model. And this gives us 3D tracks for all 26 object categories. And we also use an LLM through program synthesis that takes a natural language prompt and turns this into a generated code snippet. And using this code snippet, we can then go and filter the 3D tracks, which we get from our off-board perception system, and then figure out which tracks are being referred to, which tracks are related to the referred track, and what are all the other things in the scene that we don't necessarily care about. So this approach has many of the typical failure cases that you might expect with large language models. So not considering the limitations of the off-board perception system, we find that our baseline, which we call RefProg, struggles with semantic ambiguity. So in this case, we have a car following closely behind the bicycle, but the generated code snippet from our LLM is actually inverted. So it's actually finding the bicycle that's closely following the car. right? And we also have this limitation of a lack of expressiveness. So given the query, find a car pulling out of parallel parking onto the road, the sort of API which we define to be used by this large language model simply doesn't have the expressiveness necessary to find such interesting and complex scenarios. And I think these two limitations were a huge motivation to the winners of this year's challenge, who basically took this to heart and really tried to figure out ways of improving upon the limitations of the LLM. So this is a quote from one of the team's technical reports. The limitations of these LLMs are not merely superficial issues, but represent fundamental hurdles in reliably converting complex human language into precise and correct machine executable instructions. So I think this sort of very nicely illustrates that these are sort of fundamental problems that we as a community need to wrestle with if we want to bring to bear vision language models for the task of scenario mining. So to announce the winners of this challenge, we had 8 teams participating in this brand new challenge with over 100 submissions. So I think this is an excellent showing from the community. And I want to highlight a couple of interesting takeaways from each of these methods. So the first place, I also want to highlight that all methods adopt our sort of proposed program synthesis-based approach, and they propose tweaks to improve the performance of the LLM. So all models take as input the output of an offboard perception system proposed by a team that participated in a previous iteration of our challenge for end-to-end perception. So this is offboard tracks from team LE3D E2E. And these were state-of-the-art tracks, so it's natural that we want to use these for this challenge. So the first team, Zeekr UMCV, has 2 key insights. The first insight is that instead of asking the LLM to process each natural language query one at a time, it turns out that LLMs are sort of great at reasoning about long context. So if you prompt for all of the classes, for all of the sort of natural language queries all at once, your model is able to sort of reason about the sort of regularity of prompts and figure out how to appropriately turn everything into sort of nice executable programs. And the other sort of almost intuitive insight is that if your LLM generates code which doesn't compile, the most natural thing you can do is provide the sort of broken code and the error message back to your LLM and ask it to come up with a better prompt. And it turns out that these 2 techniques are sort of pretty important to improving on our baseline performance. So importantly, I'll sort of quickly go through the other methods because it turns out that all of the top teams had similar ideas. So the second team, MI3UCM, also leverages this key insight of iterative prompting. The third place team, ZXH, leverages this idea of batch prompting. I do want to sort of give an honorable mention to team DGIST that not only sort of uses reasoning LLMs. So in our baseline, we use Claude 3.7. They swap this out for the O3 reasoning model, and they find that this reasoning capability seems to help a bit. They also use a VLM to help with this iterative prompting. So instead of just passing the generated program back to the LLM, they also pass in RGB images of the scene, and they use that to figure out how to best tweak the generated function. Okay, so with respect to this challenge, I think in the next iteration, we'll want to increase the dataset size, make things even more diverse. But from the method side, it'd be great to see more end-to-end approaches. As I mentioned, our method struggles with a lack of expressiveness. So being able to, on the fly, generate an API to construct more informative programs would be great to see. And I think one of the key challenges is that in the real world, we're dealing with terabyte scale data, and it's incredibly important to consider runtime. So if we want to really scale this up to terabytes worth of data, we need to be cognizant of compute bounded inference. And lastly, let me quickly go through the results of the multi-agent forecasting challenge. So we've been running this challenge for about 7 years. And in every iteration of this challenge, we've innovated on the evaluation setup, improved the ranking metrics, and every year the community has sort of impressed us by continually improving upon the final performance of the model here. So just to recap, this data set is collected over 6 cities with 250 scenarios, and it's highly curated to be challenging. So we have AV relevant interactions, socially complex environments, and many non-vehicle actors. And let me sort of skip through this. This iteration of the challenge really focuses on multi-world forecasting. So in order to safely plan, one key insight is that we need to understand how not only how we move, but how everyone else moves in the world. And we need to think about how this occurs jointly. So this multi-world forecast factors. So the input here is 5 seconds of kinematic history. We know the sort of class types of all the actors, and we have a local static map. And the task here is to predict normalized probabilities for 6 futures that captures the joint probabilities of how all of these agents interact with each other. Okay, so I'll sort of briefly skip over the metrics here, but the key thing to note is that lower is better in this case. Okay, so we had over 100 submissions from 26 teams, and we had many people submit to many of the Argoverse 1 and Argoverse 2 leaderboards. And what we found was that the best performing team, IMR, which is iterative multi-world weighted regression for multi-target trajectory prediction, was one of the only teams that improved over last year's top method. So huge congrats to this team. And they were able to show a 5% year-over-year improvement on the primary metric which we used to evaluate, which is min-world Breyer FDE. And sort of to briefly talk about the highlights, they propose an iterative decoder with segmental refinement. So this means they basically break up the 6-second future trajectory into 3 components. They predict the 0 to 2 second trajectory differently than the 2 to 4 second and 4 to 6 second trajectory. And then they perform temporal attention and perform this prediction iteratively. So this temporal attention leverages the initial set of predictions to inform the next iteration prediction. And they also propose a mode world weighted regression loss, which encourages mode diversity while preserving top 1 joint accuracy. So that was a quick overview of the motion forecasting challenge. And again, we want to sort of urge the community to think about forecasting under bounded compute. And as for the Argoverse 2 data set as a whole, I think there are a number of interesting directions that we as a community can go and move forward. And as Zhan mentioned, it's critical for the community to step up and get involved. So I think this is a great opportunity for folks in the community. So I'll end with the last note that all the challenges we talked about today will remain open. So we talked about unsupervised scene flow, scenario mining, and multi-agent motion forecasting. So if you're interested in any of these challenges, please feel free to submit. And if you have any questions, the Argoverse 2 GitHub is a great place to post an issue and ask your questions. So with that, I'd be happy to take any questions. Thank you so much.
Thanks a lot for the introduction. So I also appreciate the great efforts and invitation from the organizers. So today I'm going to talk a little bit about our recent work from Berkeley Deep Drive, as well as the research team at Applied Intuition, on how we can make the neural simulation more scalable for autonomous driving. So right now, the onboard stack for autonomous driving is migrating from more modularized kind of stack into more and more end-to-end differentiable stacks. And the question is how we can really evaluate or even train such kind of end-to-end stack with closed-loop simulation, which is driven by a large amount of data that we collected from the real world. And we can automatically generate reactive sensory inputs for such kind of end-to-end stack. And actually, neural simulation shows extremely strong potential and power for dealing with such kind of tasks. And some of the representative work includes 3D construction with Gaussian splatting or generative methods like diffusion models or even world models. But actually, our expectations for neural simulation is far beyond just utilizing large amount of data. There are several aspects that we want to consider. Of course, we want high fidelity of the generation with cross-modality and temporal consistency. We also want this to be more generalizable with strong controllability as well as robustness to not so well aligned sensory inputs. we also want this to be more and more self-supervised without too much human annotations, which can be pretty costly and inefficient. And last but not least, we want efficiency to be much better, both for the construction stage as well as the inference stage. We don't want to pay too much for the GPU hours for the reconstruction of the scenes when it goes to large scale. Well, we also want to have the online inference to be with super high throughput for really train our end-to-end model. So that's why we want to make neural simulation to be more scalable, working at the intersections of that. So first, let me talk a bit about the labelless part for one of our recent work. So actually, Gaussian splatting is showing pretty strong power in converting the multi-model stream into some reconstructed scenes that we can directly utilize for simulation. And recently, there are many interesting work, including the driving Gaussian, which is utilizing 3D bounding boxes for the decomposition of the static dynamic scenes, dynamic parts of the scenes. But actually, this can be pretty costly and inefficient procedure. And our question is, how we can try to avoid having this for the 3D annotations, while still having the pretty accurate decomposition of the static dynamic parts. And that's why we propose Desire.js, which is the 4D street Gaussian for self-supervised static dynamic decomposition, which can simultaneously reconstruct the surfaces as well with the normal depth as well as the meshes. And this is what we published in CVPR this year as well. So what we are doing is decomposing into two stages. First is we implement some Gaussian splatting model to render the images from our data and taking advantage of some of the pre-trained 3D foundation model, namely FID3D, so that we can obtain some feature map for both the rendered image from the Gaussian as well as the ground truth image. And then we can compare for the feature maps to obtain some feature similarity score for us to obtain pretty accurate dynamic mask. And in the second stage, we implement some dynamic Gaussian model, namely the periodic vibration Gaussian, so that we can render some velocity map. But this map may not be super accurate, and we can try to rectify it with the dynamic mask obtained from the first stage, so that we can have the corrected velocity map, which is pretty accurate, that we can directly decompose the static scene from it. And actually, we are also implementing some regularization for the Gaussian scale so that we can obtain pretty accurate 3D kind of information. For example, we are trying to penalize the minimum dimension of the Gaussian so that we can obtain some flat disk-like Gaussians. And we also penalizing the maximum dimension so that we can try to avoid having giant Gaussians, which can downgrade our quality. And then on the right-hand side, you can see how we can obtain pretty good flat disk-like Gaussians so that we can directly utilize for recovering 3D information, including the meshes as well as the depth. And here are some quick results that we can show. And on the top side is the ground truth image with moving vehicles, pedestrians on the road, or even on the sidewalk. And by implementing Desire.js, we can accurately decompose the static part from the dynamics. And here is a quick video demo showing how good the performance is. So actually, Desire.js provides us pretty powerful tool for extracting the static parts and decompose the dynamic part from the in the 3D Gaussian reconstruction. But this is definitely not sufficient for us to create a perfect reactive generator in closed-loop simulation, because when we are trying to control the motion or behavior of the surrounding vehicles or pedestrians, there is a pretty obvious problem that we can observe for 3D Gaussian, which is incomplete views for the objects, for the parts that we haven't seen when we are trying to manipulate the vehicles with the side that we haven't collected data from to be towards us. It's pretty hard for us to render perfect kind of images. So how we can deal with such kind of problems? One of the straightforward way that we can like take advantage of will be some off-the-shelf image to 3D models that can generate some 3D assets so that we can insert into the 3D reconstruction scenes. But the problem is, for such kind of asset, the quality or fidelity may not be super high or satisfactory, and the lighting of it, either on the vehicle or the shadows on the ground, may not be super satisfactory. And that's why we are thinking about how we can deal with this problem by like enhancing the 3D asset with more realistic rendering and having more realistic shadow or lightings on the ground. So that's why we introduce R3D2, which is trying to create realistic rendering for the insertion of the 3D asset into the 3D reconstructed static scenes. And this is a joint work with our visiting PhD students at Berkeley Deep Drive. So like whether or not it's like the assets from the same scene, cross scene, or cross dataset, or text to 3D, we can enhance that with diffusion model with significant improvement of the FID scores. So here is some quick idea regarding the R3D2. So when having the ground truth images, we are trying to apply some mask for extracting the dynamic part of the images so that we can obtain like partial view of the moving vehicles, utilizing some off-the-shelf image to 3D generator to have the complete 3D assets generated. And we try to insert that into the static part of the reconstructed scenes so that we can curate some data set serving as the input of some diffusion model. And we can use the corresponding image to serve as the ground truth for the supervision. And we design some one-step diffusion model utilizing VAE-based encoder and decoder to be trained from this curated data set to enhance the rendering for our data. And here are some quick results, and from which we can see that for the shadows on the ground, it can be pretty realistic after the naive insertion and applying the R3D2. And for the lighting on the surface of the vehicles, it can also follow the like realistic kind of sand directions to render the corresponding lighting on the vehicle. And we are also allowing for more controllability while maintaining the realism, whether there are insertions from the cross-scene kind of like 3D assets or cross data sets, having some vehicles extracted from another data set inserted to the other. We can always utilizing this for strong enhancement of the rendered like quality. And there are even more controllability that we can allow. For example, the text to 3D. We can use the text prompt to generate the corresponding 3D assets and having the realistic kind of enhancement with the R3D2. And what is more important is that we can also arbitrarily rotate the vehicle with different kind of angles. For example, the 20-degree, we can still obtain pretty satisfactory kind of rendering. And some results that I want to show, even if we rotate the vehicles into like 180 degree with the R3D2, we can always enhance the fidelity significantly, either from the original reconstruction or the naive insertion that we are performing. And we also allowing different kinds of controllability for cross-scene, cross-data set, as well as the text to 3D to obtain significant improvement of the fidelity. And here is an also interesting video that we created by utilizing the Waymo open data set. So here is the original video, and then inserting some 3D assets with 20-degree rotation, and then enhancing that with our R3D2 with pretty high quality there. So that is, we are showing we can have arbitrary kind of manipulation of the 3D assets in the data set. And a few more videos that I want to show for inserting some assets created from Waymo open data set into the Panda set here, as well as some even more controllability with the text to 3D, like the prompt with small blue pickup truck to be created, inserted into the Panda set. Okay, So now we show something related to how we can utilize diffusion models for enhancing something on top of the 3D reconstruction with the 3D assets. And actually, the utilization for diffusion models can be even one step further. That is directly generating multimodality, like raw data for serving the end-to-end kind of onboard stack with both multi-view images as well as the corresponding point cloud with input conditions like 3D bounding boxes or even the language prompts. And we are trying to ensure the consistency between the different modalities. And this is a work that we published in Aclear this year. So different from some traditional paradigm, which is dealing with different paradigms of the data generation independently with the diffusion models. What we are trying to propose is to having the information exchanges between the two pipelines so that we can have consistent generation for both of the modalities for multi-view images as well as the depth information. A quick overview of the architecture. So for the two pipelines, which are denoising from the noisy range image latent as well as the noisy multi-view image latent, we are trying to have latent diffusion models to denoise that. And actually in the reverse process, for each of the step, we are trying to have the one of the modality to be conditioned on the correspondence from the other modality with the epipolar line, so that we can have the VAE decoder to directly decode either the synthetic range image or the multi-view image with pretty good consistency between each other. And here are some quick results that I want to show with the input conditions from 3D boxes, as well as some text prompts depicting the location, depicting what kind of scenario it is, or some potential behavior of the vehicles. And we can see that the model can generate pretty good consistency across different multi-views of the cameras, as well as in between the point cloud modality, as well as the multi-view camera modality. And some similar kind of situation settings that we have for different kinds of prompts or bounding boxes to be serving as the conditions, and they can still obtain pretty good performances there. And we can even go one step further to control the styles for rainy, for sunny, for night kind of style, or even having different kinds of number of the bounding boxes to reduce that into a half or increase the number with extra ones. And we can obtain the consistent kind of cross-modality consistency perfectly as shown in those kind of images as well. Okay, so now we talk about how we are dealing with different kinds of perspectives for the scalable neurosimulation from the quality perspective as well as the labelless perspective and address controllability. And now let's switch the gear a bit for the efficiency side, as well as more about the generalizability, especially towards the 3D reconstruction kind of scheme with Gaussian splatting. So the work that I just mentioned, either the Desire.js or R3D2, the 3D.js methods that we are utilizing is based on Bayesian optimization kind of paradigm, which is trying to optimize the Gaussian parameters directly for each of the scenes from the data that we have. And such kind of paradigm, when we are thinking about different attribute, different perspective of its attribute, from quality perspective, yes, it's pretty good. And from efficiency perspective, it's not so satisfactory because it takes at least 1 GPU hour to construct each of the scenes. For generalizability, it can only construct something that we have seen from the data log. And it can also be super sensitive for not so well aligned sensory input. And that's why we are thinking about how we can bring in some of our insights that we have learned from the onboard perception or other kinds of model design, so that we can create some feed-forward network that can directly output some like key parameters of the Gaussian ellipsoids, and from the historical frames that we have obtained. And such kind of paradigm could have good potential for much better efficiency than the precision optimization paradigm, although the quality is still to be improved. And for generalizability, it's also enabled with large amount of data trained with this one single model. And it's also can be with better robustness for unaligned sensory input. And due to the limit of the time, I will just briefly mention some of the representative work for feed-forward Gaussian for applied to the autonomous driving. For example, driving recon, we're trying to introduce the 3D aware positional encoding together with the temporal cross attention with the Gaussian adapter decoding the parameters of the Gaussian with the feed-forward model, large feed-forward model designed for the autonomous driving applications. And we can see that for the Gaussian parameters that we obtained and then reports into the images for the objects and the scenes that is pretty far away from our ego vehicle, it can obtain much better performances than the other state-of-the-art feed-forward models for feed-forward Gaussian models for autonomous driving. And here is a quick view showing taking three like frames as the historical ones, putting that into this feed-forward model, how we can generate the Gaussian parameters when render that for each of the time step. And they can even with some more generalizability, although it's with like pretty low resolution due to the limitation of the computation as well as the large size of the model. So there are still like rooms for us to improve, especially considering the efficiency perspectives. And there is also another feed-forward Gaussian work called Pixel Gaussian, which is trying to challenge the uniform assignment of the numbers of the Gaussians to each of the like image space pixels, so that we can take advantage of the existing uniform pixel-wise paradigm. Some Gaussians, we are just utilizing that as the initial ones to be optimized as cascade Gaussian adapter, which can either split the Gaussians into more like numbers or prune that to reduce the numbers, then with iterative Gaussian refiner so that we can obtain the Gaussians that can be adaptive for the numbers of different areas in the images. And it can be pretty clear that when taking a look at the areas of the images with more textual information, we need more numbers of the Gaussians. And our proposed method can obtain better performances than the other feed-forward Gaussian like methods. And there are some areas which is pretty simple with the textures, and we need less numbers to review that. And for a simple like table surface, it can also be with much better performances than the other method. Okay, so after talking a little bit about feed-forward model, actually let's go back to an even like higher level view, talking about how we are designing the models for both the onboard and offboard tasks, including the onboard differentiable stack towards tasks like perception, prediction, planning, or mapping. Some models that we can design for the feed-forward generation of the like reconstruction parameters, or even towards like more generative models or auto-labeling side. So for feed-forward Gaussians, we are taking advantage of many insights that we obtained from the onboard model design so that we can facilitate for more generalizable and efficient reconstruction for the offboard tasks. But let's think about it from the other way around, whether we can take advantage of the representation from the offboard construction side so that we can facilitate the onboard tasks as well, so that we can work towards some unified model design, model structure design, as well as unified 3D representations for both the onboard and offboard tasks. And this is also some thoughts that we have for paving the path towards some foundation models that can facilitate both the onboard and offboard tasks. And this is actually like pretty recent work that we have done at Applied Intuition research team from our research scientist Yihan, as well as two intern students from Carnegie Mellon and Berkeley. So actually, we are trying to address this thought from dealing with some challenging onboard task, which is occupancy prediction, which is having the most like fine-grained semantic information for the 3D onboard task. We are trying to take advantage of something we have learned from onboard side, that is having the sparse queries to obtain pretty strong runtime efficiency. And we are also like exploiting the like streaming structure, considering the temporal inherent temporal nature for the data that we are dealing with. And we are also utilizing the representation from 3D Gaussian perspective for pre-training so that we can obtain much better performances. And for the occupancy prediction task, it can obtain much better performances than other state-of-the-art methods, as well as having much better kind of runtime efficiency. So here is the general architecture that we designed for the S2Go. So there are some it's a streaming architecture, and we are taking some past 3D queries, which can be pretty sparse. And our temporal transformer is taking such kind of queries together with the encoded features from the current images, as well as the randomly generated new 3D queries to generate the queries for the current frame. And then we decode that into like Gaussians that can be predicted and render the corresponding images. And we then split that with the Gaussian to voxel splitting into the occupancy prediction so that it can be supervised. But if we directly train such kind of architecture from scratch, actually it yields to some not so satisfactory performances, which is not quite comparable with the other state of the art. So we are thinking whether we can introduce another stage, which is the pre-training stage, that we can either randomly generate some noised kind of input for the 3D queries, so that we can have the denoised queries kind of pre-training together with the rendered depth maps and RGB images from the predicted Gaussians, utilizing the 3D reconstruction kind of thoughts that we have for the neural simulation, so that we can have much better performances than the previous ones. And here is a qualitative kind of intuition that we can show before and after the pre-training. The opacity of the Gaussian centers can be much more strengthened with the stage, and the performances of the occupancy prediction can go from not so satisfactory level directly to a pretty strong level. And such the S2Go structure that we propose can also obtain pretty strong performance even with the monocular camera kind of view on the KD 360 dataset benchmark. So compared with the other state-of-the-art methods, we can obtain much better performances for the occupancy prediction. And on the new scenes benchmark, similar kinds of story, much better performances with even better kind of runtime efficiency. And actually, the sparse queries can also help us allow for keeping pretty clear, good separation of the objects for the 3D occupancy prediction in comparison with the Gaussian world. We can directly and clearly separate the objects for the 3D in the 3D perspective. And here is a pretty long video that I won't play all across, but you can see that in comparison with the ground truth video on the right hand side, the occupancy prediction with our proposed structure, taking advantage of the 3D Gaussian representation, can obtain pretty impressive results. Okay, so in addition to those methodologies that we have proposed, actually in Applied Intuition, we also productionized the neural simulator with the 3D Gaussian splitting kind of methods. which this is like a scene that is like near our headquarters. And there are also like corresponding like point cloud that is generated simultaneously. There are different like countries that we are generating the neural simulation kind of reconstruction, or even with off-road kind of like scenes that we are generating. And I will also appreciate 30 seconds from you for having a quick promotion for our hiring. We have a research team working on different kinds of like research topics, including neural simulation, world model, foundation model, reinforcement learning, post-training, as well as even agent AI and robotics. Actually, yesterday we also announced our partnership with OpenAI for different kinds of like exciting kind of topic that we can work on. And we are hiring for different kinds of roles for the research team, as well as for our product team for neural simulation, for onboard stack, as well as ML infra. So a quick conclusion here, what we can have for the takeaway. So we are thinking about how we can make the neural simulation to be more scalable from 4 different perspectives, including the quality, generalizability, labelless, and efficiency perspectives. And we are also thinking about how we can unify the model design and the 3D representation for both the onboard and like offboard tasks, so that we have working towards the foundation model that can be utilized for different kinds of tasks with large amount of data that we can obtain from the real world, so that we can have super efficient kind of inference for this model to serve either for the offboard construction as well as the onboard inference part as well. So I think I'm just right on time, and I'll just stop here for any questions from you. Thank you.
So this is the team working on this project. Basically me, Zhan, Orly, and Trevor, our chief scientist, which is also professor at Berkeley. And I think we are all here at the conference, so feel free to reach us if you want to know more. So I will start to speak a little bit about Nexar, the open data set that we shared in the beginning of the year. A little bit about the challenge, the leaderboard, the winner solutions, and then we'll share some insights. So Nexar started 10 years ago with the mission of making roads safer. And we start doing that by producing dash cams that you can install on your vehicles. And early on, we started detecting every kind of incident like hard brakes, harsh cornerings, and so forth. And every time we detected that kind of event, we recorded a video on our cloud. So today, we have over 350,000 cameras in the US installed on our customer base. And we have recorded more than 60 million videos of these kind of incidents. And we are working in several fronts, like 3D reconstruction and so forth. But the most related with the work presented here, it's related to how do we search this large database of videos to look for edge cases, collisions with pedestrians. So everything that might be of interest, especially for the AV community. And so the focus of this competition was on traffic accidents, which cause significant loss of life and financial damage. We believe that with our massive collection of videos, we can help the AV industry moving forward with the anticipation of these kind of cases and reduce the fatalities. So the question we start by doing ourselves is, can we help anticipating collisions with the front camera only, because that's what our dash cams have. It's a front-facing camera, road-facing camera. And we looked into a sample of 2,000 collisions. And we found that most of them happen on the front of the agro vehicle. And most of them were also between cars and trucks, between cars or cars and trucks. So this motivates us first to release an open data set. We try to provide high quality videos and also show a bit of what our database looks like and to help advance the research on this important problem of collision anticipation. So about our data set, it's 1,500 high definition videos, each with about 30 seconds. And we covered most important US cities, and we tried to cover also different weather conditions, lighting, and different scenes like urban, suburban, highways, and so forth. One question we had was how to annotate for temporal events, and we looked to some of the data sets that are out there released in the community, and we find that most of them either have the time of appearance, which is the time when you see the third party for the first time, which, for instance, in this example video, it's at time 0. And we didn't find it to be super helpful for what we wanted to do. Or we also see the time when the collision is imminent and there's actually nothing you can do. So we proposed, in addition, of course, to the time of collision, to also add the time of alert, which is, it's rather subjective, but it's something that when should you take action? When is the moment that you understand that some action should be taken, like hitting the brakes or the wheel? And because it is subjective, we asked 10 annotators to annotate for each video this time of alert. And then we adopted a conservative approach where we went for the second shortest interval. And you understand why, because we use this time of alert to understand how far in time is an accident predictable. So this is the distribution of the alert interval. We get the alert interval by subtracting the collision time and the alert time. And so this is the time of reaction. It's the time you get to react to a potential accident. And we see that in our data set, we have some samples where this time of reaction is under 1 second, which can be too much for a user. So if you send a beep to a user for a user to react, but because we are targeting not only aftermarket devices, but also autonomous vehicles, which can have shorter reaction times, we left these accidents which are more difficult to predict in the data set. So this is looking to the challenge. This is an example of a video on the test set. So basically it's a 10-second video, and the video stops at a given time, and the model should say how likely it is for an accident to occur shortly after. And as the goal, we want to predict accidents as early as possible, while minimizing false positives and maximizing recall. So looking to the literature, we saw that these were also the typical goals of the papers out there, but we found that these were split by 2 metrics. One typically dedicated to the time to accident, so how much time in advance can a model predict, and another which was related to the precision and recall, typically the area under the curve or the average precision. And here we propose to use a mean average precision, which tries to unify these 3 goals into a single metric, which was also important for ranking our leaderboard using a single score, single metric. So how do we do this? Basically, we define 3 thresholds, 500 milliseconds, 1000 seconds, and 1500 milliseconds, which are how much time in advance, how much time you before the accident you cut the video, And so, of course, if it's 500 milliseconds, the accident will happen shortly after, in the case of a positive example. If it's 1.5 seconds, it's probably more difficult to predict because you have 1.5 seconds until something happens. And so we take this, the average precision of at least 3 thresholds, and we find the average, the mean of the 3. One important aspect to point out is that we use the alert interval to understand if a given video can be cut, for instance, at 1.5 seconds. If we have, for instance, a reaction time of 1 second, that video cannot be made part of the average precision curve of 1.5 seconds, because at 1.5 seconds, that incident is not yet predictable according to our annotators. So regarding the participation in the challenge, we had almost 300 participants and over 1,600 submissions on a challenge that was up for 12 weeks. Well, and we were quite happy with the adherence. And as a leaderboard, on the first place, we have Paul Anderson. Paul Anderson is actually the CEO of a company, 3 Lines of Code, which has a booth here in CVPR, and I just talked to him. He's currently not here, but he will be also demoing his solution for this challenge in his booth. On the second place, we have 2 students from China universities, and on the third place, we have an independent data scientist. So quite diverse top ranking. We also have honorable mention to a team from the Yuan University, which got a very high score also, but there were issues in their submission, so that we had to leave them out, but their approach was quite interesting. So looking to the approaches of the different teams, on the top 2 places, we see a trend where using video transformer models had the best results. On the third place, we saw a simpler approach based on looking into the optical flow and using convolution networks. And another popular solution that we see was looking to the frame as individuals and getting some kind of encoding or embedding for each frame, and then trying to use a GRU or other recurrent neural network to capture the temporal aspect. And by the way, this was also the solution proposed by ChatGPT when I asked him how do we solve this challenge. So, and it was quite popular. So I'll speak a little bit about the main, the top 3 places. So in the top 3 in the first place, we have a video transformer, not a large one with 35 million parameters. And here, the main advancement was done by using the 3 Lines of Code tool to inspect the instances, understanding things like confusion, where are the areas where are confusions between positive and negative examples, some of those examples, weighting the instances, and so forth. So with this kind of iterative refinement of the training data, Paul was able to get from 0.7 to 0.9 without any fine-tuning or any manipulation of the network. On the second place, the team used a much larger video transformer with 1 billion parameters. And they did the full model fine-tuning with the training data we provided. And one interesting thing to point out is that there are a lot of decisions here to be made. Decisions related with the sampling. So where do you start sampling the positive examples, how far, also balancing strategies, because you can use the positive videos for both getting negative and positive samples. And the team didn't explore that too much. And so we believe there is potential for this model also on optimizing these decisions, but also if we feed more data, we should also see higher returns. And finally, on the third place, basically the team used simple UML to get the vehicle masks to do the segmentation, and then optical flow by calculating the differences between two frames. And this was enough, together with two ResNets that were ensembled, to provide a score that was not very far away from the rest. And this was like inspired from the Dutch theoretical relevance examination, where students are presented with a single image and they need to decide what to do, if they will hit the brakes or if they will continue driving or any other action. Also, the solution is a complex. Here it's very simplified because the author uses several instances and does an ensemble. It doesn't only uses 2 frames. So we analyzed the top 10 teams, and basically we optimize, we transform the submissions of every team so that we can have binary decisions for each team, and we calculate the difficulty score as, for this video, how many teams failed classifying the video. And so this will give you a difficulty score between 0 to 1. And one study that we did was comparing how much more difficult it is to predict 1.5 seconds in advance versus 0.5 seconds. And we see kind of a linear relation. This is very limited to the three points in time that we are measuring. So, but still it's interesting to quantify that having 3 times more time in advance makes the problem 3 times harder, according to our metric, to predict. Another insight was that the teams have much more difficulty in setting highways. So we have 25% failing on urban scenarios versus 16% on highways. And fog was super challenging. We didn't have a lot of examples with fog, but every time we had fog, the teams failed. So there are some difficult cases across all teams. These are all just examples. So you see the vehicle that is crossing a red light. And this is the kind of video that teams had difficulty. So most of the teams failed that video. This is another one. You'll see a car that is leaving the parking, and this will result in a near collision. And most of the teams also didn't see that. Here's another one, and on the right you will see a vehicle leaving the parking, and it's subtle because it's very difficult to predict. But still, it's interesting to look to some of these examples and try to understand. And this is a very recurrent pattern, which is the car on the front brakes, you start braking, and we don't know if this will result in a near miss or a collision, or if it's a normal, regular driving situation. So where next? So we'll be at ICCV in the Too Cool workshop, where we'll be presenting the method that we are developing in-house. We are also hosting a workshop in Porto, Portugal, in the end of the summer, probably. So stay tuned. We will have the first place they are presenting their solution in more detail. And we also have invited speakers and some of in-house speakers. Just yesterday, we released the test set that we used on the competition. including annotations and a script that allows you to evaluate your own solution in a very simple manner. And we're also looking into the ML dataset, annotating the alert time so that we can extend the dataset and apply our metric there. So key takeaways. So we've introduced the alert time, which we found to provide interesting and useful insights. We introduced the mean average precision as an unified metric for tackling recall precision and time to accident. We released an open data set, including a test set with ready-to-run evaluation, and we provided insights on key solutions from the community in this challenge. So here are some useful links, the blog post that we wrote about this, the data set that's on Hugging Face, the competition that's on Kaggle, and reports from the winners from the first 3 places. And that's all, folks. Open to questions.
Hi, everyone. I'm Chen. I lead the perception team at Waymo. In the past year, Waymo has made a significant progress in terms of the number of trips that we serve. Today, I want to talk about a few really important problem areas while we're scaling the product significantly in the past couple of years. You know, today, for nominal driving, there's really not that much challenge anymore. So today's system for nominal driving, the system generalized really well if you go to different geographical locations, and even if you move the system to a different vehicle platform, it is really a lot of the long tails and that matter in today's situation. And that's why I want to talk about those problems, which can be lesser known, because Waymo pretty much is the only AV company who have such a large scale of development. And I would also want to encourage you to work on the harder problems, because those are what that matter to an actual product. Okay, just a very short intro about the scale that we operate. It's a very short video. Today, we have about 250,000 trips per week. That's about 1 million trips every month. To make sense of the scale, last year, 2024, the whole year, we have served about over 4 million trips for the whole year. And now we are already at 1 million trips per month and still accelerating. So we're in a pretty fast pace of increasing the scale of the product. Going to the next one. Okay, great. So in SF and Phoenix and LA, right now there's no wait list. So you can go there and download the app and take the ride. This is a pretty convenient. That also brought a lot of visibility to the product, because anybody who dropped by those cities can experience the AV rides. In Austin, we partner with Uber. So if you hail a car from Uber app, sometimes you'll get a Waymo car. You can also select that you want to prefer Waymo car, so you have a higher chance of getting it. Expanding in Silicon Valley as well. And also Atlanta, we also partner with Uber, and that will open to the public users soon as well. And next year, 2026, we're going to bring Waymo 1 to Miami and DC. And here's a map showing all of the cities we are operating and going to open operation, and all of the cities we've tested, including the 10 road trip cities this year. And also Tokyo. We've had a few cars arrive at Tokyo, start doing data collection there already. So Waymo's mission is to build the world's most trusted driver. What does that mean? So given 1 million trips every month, basically our cars see all kinds of situations every day, every week, every month. The scale is very large. So it takes a strong commitment to both the technology and also the whole product to make sure at this scale, the product really bring a safe experience and bring also a comfortable user experience. So user want to come back and take the car again. To give you some examples, This is a compilation of a recent events. In the first one, you can see the motorcyclist bumped into the middle of the road and fell, and we needed to respond to it very quickly. The second one is a cyclist rushing through the slope, and we detected and stopped in time. Also, red light runner. This one is a scooter fell. I think there are a couple more. This one is a car crash right in front of us. This is a nightlight, a red light runner, where we detected early enough and stopped and nudged right in time to avoid it. Okay, so this is a recent safety research paper that's published in a journal where by looking at over 56 million miles that Waymo driver has driven, the Waymo driver managed to drastically reduce the amount of crashes involve severe injury, including pedestrian, cyclists, and motorcyclists. And to achieve safety, it is not just about the software. It's not just about the models, the system running on the car. The hardware system also have a, carefully thought through redundancy built into the whole system. For example, redundant power systems, braking, steering, compute. All these matter because at a large scale, you have to make sure the hardware faults are not causing a big trouble to the product. And a lot of the times for transient hardware failures, we also have the ability to recover so that the car can still move forward without being too much impacted by these transient failures. And of course, the strongest momentum to push EV technology forward has been the advancement of ML. And starting from the very early days, we started using the DeepNet and also continuously using SOTA technology, and the onboard stack changes very rapidly all the time. So in order to scale to different geographic locations, different platforms, sensor suite, and compute, we build a Waymo foundation model and distill it onto onboard systems. And through doing this, we can have more generalization power from the foundation model, but also being able to quickly adapt to an onboard system that can deploy into different platforms. And this foundation model encodes all of the sensor data, including all of the cameras, radar, and LiDAR, and also have a world knowledge built in and decodes all of the driving relevant tasks, including perception behavior simulation. I think this you are familiar with. But what I want to say is that, just having a foundation model doesn't mean that it can readily solve all of the problems that we need to solve. Foundation models it has a great generalization power, but for us, the way for it to be really useful is not only does it generalize, but also it should come out of the box, solve most of the long tail issues that we care about. Otherwise, you wouldn't be able to leverage the model and distill into a powerful student models. But also during the distillation process, it is very critical that we can keep all of the generalization while you go from a large teacher model to a smaller student model, and better yet, keep all of the zero-shot capability, which is also not easy to achieve. In addition to that, when we produce the student model on the car, it really have to fine-tune and solve all of the data slices what we care about, solve all of the long tails we care about. That's a very high requirement there too. So in the rest of the talk, I will quickly go through a few problem areas to give you a sense of what are the problems. First one is weather. Since around mid of 2003, we had a zero weather-related downtime in SF and Phoenix. That is pretty hard to achieve. That means basically we can drive through all of the dense fog situations in SF and also the monsoon in Phoenix. I have a video here for the monsoon. It is a very heavy rain and heavy wind, and you can see there was a pedestrian walking on the sidewalk, which is not recommended. So we are able to differentiate what are the weather situation and recognize all the objects correctly. As you are approaching, you can see the wind is getting really strong. And we have been operating this situation for over 2 years now. Next one. So it is, so one thing is you have to drive through rain, but also after rain finishes, there's all kinds of road conditions that we also handle. So this is one example with a puddle. So when there's a puddle, we detect where the puddle is, the size of the puddle, and in this case, we decide to lane shift to the left to avoid the puddle. But there's also flood, which doesn't happen all the time. We've only seen only a few hundred of them, which is way less frequent compared to many other phenomena that we see. So this is a pretty long tail. And however, the requirement on both precision and recall are very high. Let's say if we have false positive flood, then it can really impact where you route and whether you get stuck in such situations with a false positive. However, if you have false negative, then it's not great to drive through a flood. It can be pretty scary. And we've seen it in all the geographical locations, especially this season. There are a lot of rain in all the cities. And when we look at flood, it's not enough to just see, oh, there's water. There's also the depth of the water. So it requires a lot of context information to know if there's a flood or it is a puddle. So we use VLM so that really we need to leverage the world knowledge so that we can handle the situation with a few shot learning. So here's one simple example with a parking lot with a standing water, not super deep flood, and we're able to detect there's a flood and do a multi-point turn and exited the parking lot from the other direction. So snow, we're working on snow. So it is very interesting because it's also pretty demanding on the vehicle hardware as well. These are a few examples from the data collection that we did this year from Truckee. It's the Lake Tahoe area. And the snow accumulates pretty quickly on the car, so it can block all the sensors very quickly. So for the sensors, there are both heating and also cleaning so that at least you can see. Here shows a video of the wiper on the cameras, which is pretty cute. And you also need to be prepared that the sensors can get fouled anytime. Here are the two examples from below. And whenever sensor get blocked, we need to clean it, detect it and clean it quickly. And also the models and the system need to still operate while the sensors are fouled. And this is an example where we drove in a snow condition. See, this is in Detroit. And there are some snows in the air. The road condition is not too bad. And the cameras are fouled, as you can see, but this level of fouling is not too much a issue for the system. But still working on it, especially for heavier snow conditions. So with this one, I want to show that one of the big challenges of solving snow is where do you drive? Does map still matter? And even if we know the map, in these conditions, the other drivers don't know the map. So you really have to just understand the situation and look at the other agents and decide how to drive. Sometimes there are tracks on the road. You want to decide to follow it and not follow it. And when there are buildups on the snow on the road, also we need to understand, is the buildup really deep? If I drive through, will it cause damage to the car? And also estimate the friction so that we can give the right signal to the motion control. And sensor fusion. So this is an example of video where it's a high-speed road. There were two pedestrians climbing over the barrier from the left side. I've seen this video many times. I still cannot see the pedestrian in the camera image. But you can try here. But I have another slide just to highlight where they are from the camera. So it's an overlay of the object on top of the camera image. It's very hard to see those pedestrians. I have another similar example on freeway as well. you want to watch on the right side. From the top, you can see there's a white box showing the location of a car, and you can try to see if you can see it from the camera image. It's also extremely difficult. So I have another slide just to highlight. There's a car over there on the shoulder, completely dark. Another example, this is a dust storm in Phoenix. Phoenix have monsoon, also have Haboob. When Haboob happens, you have a lot of dust. And if you look at LiDAR, you can clearly see a pedestrian on the right side. And this is important because this pedestrian is pretty nearby, and we will need to leverage different sensor modality to be safe in those situations. And I want to talk about occlusion, and this is a very critical problem, and we see it all the time. Think about when you drive, there could be agents coming from invisible areas, occluded areas at any time. And this is very important because even anticipating where agents will come out from occlusion will help us drive safely and also respond fast. I'll show you some examples. This is a bus, and there will be a cyclist coming from behind the bus. Here's another one, and there's a person running out from the building, and we detected and stopped, heartbreaked. Here's a similar one. There will be a cyclist, a child cyclist coming from the left side. These are often also pretty common. So occlusion reasoning means that we want to reason about object existence and also states in the regions where we cannot see them. And it is critical to driving safety. As I talk about, they are very, very common, and we need to be able to anticipate and respond fast. But these events, this problem also is very low likelihood and can be very high severity. For example, in the occluded maneuvers, while we are trying to make an unprotected turn, there could be a speeding vehicle coming out from behind another vehicle. And when we drive around large trucks or buses, very often there could be cars and cyclists or even pedestrians behind them. And similarly for occluded pedestrians. And this problem is very hard because one is that it is not well defined. It is not something you can infer from sensor observation. In fact, it's the opposite. It's when you infer something without a sensor information. And also it's not deterministic because it's a likelihood. It doesn't always exist. An object doesn't always exist. If you want to create a benchmark for occlusion, it's hard because you don't have a ground truth. You don't know. Even if there's no object, we still want to know there might be so that we can still behave in the right way. It's subjective because even for human drivers, some of them are more conservative, some of them are not. And there's a diversity in the agent. There are cars, pet, and cyclists, because for each of them, they can show up in different places, and also we have different state estimation for the potential occluded object. Highly contextual. I've shown a few examples depending on the time of the day, the scene, and the location, and the prior for where object could exist is also different. So fundamentally, we want to have a probability estimate on the occluded agent based on what we observe and based on what the sensor file is. So the first step is that you want to estimate object prior. And how do you do that? One part of the object prior comes from learning all of the statistics from the driving data. So you can learn in this situation, that situation, what is the likelihood that I have seen an object. However, the really useful one is that you can also use slide sensor cues to really boost your prior. So that will really help you react fast for such situations. And the second step is that we also use SensorFolv to eliminate the obviously not feasible ones. So not only object existence, knowing the speed prior is also very important. I want to show this video. This one, there will be a red light runner from the left, and we detected early and stopped, but the other car, hit with this car. For this one, the way it's relevant to occlusion is before the speeder shows up, it's actually occluded by two other vehicles on the left side. So we don't, from sensor data, it's hard to see the speeding car early enough. But because of the occlusion, we always know that very likely there could be a car behind it. But here, the key is, what is the speed prior that you give? If you give a very low speed prior, then you might be moving forward too much and get to a position that's unavoidable with a collision. But if you give the speed prior too high, then we're never able to make progress in any intersections. So there's also a lot of care into estimating the speed prior for different situations. And scene understanding. I want to show you a few scenarios where the overall scene understanding matter a lot. So a typical one is a construction. This is a simple construction scenario where we recognize the sign. It shows a slow, not stop. So we move forward and reason about the geometry of the driving. There's a cone, so we should move to the other side of the road and move forward. It's a simple construction. And there are some cases where the scene understanding is not static. For this one, it really depends on the gesture. So at the beginning, we were stopped there because the traffic officer had a stop gesture for us. And after the traffic officer stopped the other vehicle, he did signal us to go left. That's when we start moving. So this means that you have to respond to some signals that are more dynamic. See, these are really cool. These are the active incident scene cases where there could be an accident. There are a lot of EVs, and we need to reason about the scene and do the right thing. Here's the one where we know the right lane is blocked. The straight lane is also blocked, and we were waiting for the other fire truck to exit, to finish the turn. And after that, we decided to turn left. And there's another one. Okay, this one is on freeway. There's a accident to the left side. There are many EVs actually. So pretty early on, we understood that the left part will be blocked. So we did two right lane shifts. Here's one, and we did another one to move to the rightmost lane and started to merge with the rest of the traffic like this. And as we drive along further, you will be able to see to the left side, there's a car crash and many police vehicles and many officers over there. And we continue to merge with the rest of the traffic and move through the scene pretty smoothly. So in those type of things, the question here is how do you solve them? So usually you see all kinds of objects and attributes, even caution tapes. Believe me, it's a very critical object type to recognize. So the question is, if you recognize all of those, is it sufficient? It's not sufficient because then you still need to make sense of what type of scene that is, and also make sense of the geometry, and also understand, should I interact with the officer, or I'm confident with the geometry, I should just go. So all these come into the totality of solving this problem. And obviously here, the object representation is not sufficient. And the question is, what kind of representation you want to build to solve this problem? Or should you do end-to-end driving, just understand the scene as a whole and decide where to drive? Next, I want to show a few slides about the data. Data is very important. And, we drive millions and millions of data, accumulate all the miles very quickly. it is very important to have a large amount of data, but you also don't want to just use all of them because then your training becomes inefficient and you're not focused on learning the right problems. So it is very important to select the most relevant data. So we put in a lot of effort into making our data curation system really well. So we have a list of different technologies, including language search, embedding-based search that works for both appearance and also behaviors, few-shot learning on the fly while you search, and active learning, and many more. To show you some examples on the image side, here's some examples that are very typical, all pretty relevant to driving, and they are debris, fireworks, fire hazard, and different type of VRUs cases that we care about. We also have the video search capability. These are also very critical because some of the events you need to know the video to make sense what the event is. Here you see a car collision. These are all from our real driving data. Car collision, car drifting, and wheelies. Wheelies is very common as well. And for the product scale, a depot is one part most people don't know about, but I think it's very cool and it can give you a lot of efficiency. I want to show a couple videos to illustrate the idea. This is a picture of the Tolan depot in SF, where you see the cars are charging. And so the way it works is when a car goes past to a depot, you see on the dome, it shows the car and what kind of operation it needs. It'll drive to the station for charging or for ops to take a look. In this case, the car drives automatically to a charging station. And right now, we still need a human to plug in and plug out. We don't have a robot. So that shows it. And after car is charged, it'll just go out automatically by itself to serve more users. And recently we built up a factory in Mesa. So this one, the cool part of it is after the car is assembled with all the sensors and also the compute, it goes through a list of checks automatically, and then it drives out by itself to serve the user. So from driving out to serving user, it takes as little as 30 minutes directly out from the factory line. Last but not least, I want to show two really interesting videos that shows fast real-time decisions. And the first one is you can see the car cuts through. What's interesting about this is, if you look very closely, we first decided to nudge right and also honked at the car. And then quickly we decided to go to left because the car didn't really yield. So that's the really fast decision-making over there. Here's another one. You want to watch for the black cars to the right side. There's one car overtaking the other one, causing it to hard brake. And then afterwards, a hard brake again, and we dodged it, like at really close distance. There are actually many examples like this. Let me show you again. This one. Look at the black car to the right. Yeah. And that's all. And if you're excited by these hard problems, please come talk to us. And there are actually many other hard problems that we need to solve. And many of those can also benefit from a technology improvement and also, all the evaluation, everything simulation, so that we can solve them even faster. Yeah, and thank you.
My name is John Gorman. I'm a technical program manager at Waymo. Chen just described how Waymo is advancing its ability to scale in the real world. And now we'd like to talk about how we're using that experience from our scale to also enable the broader AV community to engage in fundamental industry research areas and how you can get your hands on real-world Waymo data for your research. In this session, we'll provide an overview of the various Waymo open data sets and our benchmarks. And we'll also introduce the latest updates from 2025 and dive into each of the challenges from this year. We've invited some of our top performing teams from the challenges to present alongside us on their methods. So the journey to fully autonomous driving is a story of shared innovation, and we are deeply aware that we stand on the shoulders of giants. Decades of foundational research in computer science and machine learning have paved the way from what we do today. And that is why we are proud to offer the Waymo Open Dataset, which is one of the most comprehensive and diverse collections of autonomous driving data to give back to the research community and continue to drive innovation in this space. We started with our perception dataset, which we first released back in 2019. It contains data that's suited for perception tasks, like detection, tracking, and segmentation. The initial release for our motion dataset was in 2021. It's a relatively large dataset suited for prediction, planning, and simulation tasks. We continue to make incremental improvements on these datasets. 2025 was a big year for us. Alongside hosting our 6th annual Open Dataset Challenges, we released a neat end-to-end driving dataset, which contains camera data that is particularly suited for fine-tuning vision-based planning models on long-tail scenarios, similar to what Chen just featured in her presentation. And we'll provide more information on that in just a minute. Since we've launched the Open Dataset, 53,000 researchers have used it as a high-quality tool to explore topics in autonomous vehicles, robotics, computer vision, and other machine learning more broadly. And in the last 6 years, there have been 4,000 academic papers published either citing the Open Dataset or using it as a benchmark for their research. And speaking of benchmarks, we maintain the most comprehensive set of benchmarks for various tasks relevant to the autonomous vehicle research community. Based on our perception data set, we have benchmarks covering various detection, tracking, segmentation, and pose estimation tasks. And based on our motion data set, we have various prediction and simulation benchmarks. This year, we added 2 new benchmarks, the scenario generation and vision-based end-to-end driving, which leverages our new end-to-end driving data set. And my colleagues will discuss these new benchmarks in greater detail later. So this here, our 6th annual round of challenges, we featured 2 new challenges based on those benchmarks. And we also like to rerun challenges from previous years to observe improvements and approaches from the community. And this year we ran our interaction prediction challenge for the first time since 2021, and our sim agents challenge for the 3rd year in a row. And lastly, before we dive into the challenges, we're very proud of the engagement that we got this year. We've had a total of 128 teams participate in the challenges, which is about a 34% increase from last year. We had 935 total submissions, which was another 30% increase from last year. And we had 70 leaderboard submissions across the 4 challenges, which is over 50% more from last year. And lastly, while we don't collect detailed demographic data from everyone who submits to our benchmarks, just within our community of potential finalists, we had over 10 countries represented. Okay, now I'll turn it over to Hongyang to discuss our new end-to-end data set and challenge.
Yes, thank you, John. Hello, everyone. I'm Hongyang, research science and Waymo. So let's talk about our new challenge this year, the vision-based end-to-end driving challenge. So what is this challenge about? Our traditional AV stack, we already have perception, localization, prediction, planning module with different sensor modality like LiDAR, radar, camera. But in this challenge, we ask the participants only use cameras and ego states and approach the future weapons directly. So why does this topic was exploration? First, it has really good scalability. You just drive around city with camera, with GPS, and then you collect the data. There's no hidden annotation needed, right? Second, it has a natural synergy between the multimodal large language models and end-to-end driving. There are a lot of research has shown like by leveraging the more knowledge of MLMs, we can solve these long-tail scenarios in end-to-end driving. So to do end-to-end driving research, we need a good benchmark. But the current existing benchmark, like data benchmark, are really too simple. Like Dataset using or CVPR'25, they are really just have nominal data sets. But what we really want is some long-tail data set, as Chen mentioned before. And also, we need a good new loop ER metric. So AD is definitely not good enough. And NavSim is good, but it requires the object annotation. For long-term scenarios, they usually has some real objects, which is hard to annotate. So that's why we launched this challenge to fill these two gaps. So in this challenge, we launch a new exciting data set that is featured 12 hours of ultra-rare driving scenes, capturing scenarios that occur with less than 0.003% frequency in daily driving. What does that number mean? That means you may not even see one scenarios in your whole life during your driving. So let's take a look at some examples. First, you can see birds flying, but have you seen a flock of angry birds rush to you during driving? You may see deers cross the road, but how about 3 deers in a row at night and his residence area? This is super rare. And this is a safety critical scenario. A scooter is falling down, and we build a nest serve to save her life. More than say like AI can save people's life. Now it's a time to test the algorithm. And this one is super complex. So this is a marathon. You see a lot of traffic cones. You saw people doing marathon, and the traffic light is right. And the traffic man asks you to go through actually. So this will be very confusing for any AV system. And this is another simply critical one. There's a vehicle here doing very aggressive cutting, and you need to respond correctly to avoid any collisions. Here's a life or death scenario. There's oncoming vehicle in the same lane in the opposite direction with very fast speed. And then there's a police car is chasing it. So I think this is something you can only imagine in a movie, but here's it. So as you can see, all these 6 videos are super rare. But we have 4,000 such videos in this release. And we have 3 different sets, training, validation, and testing sets. For training and validation, we have 20-second videos with driving logs. And for the testing sets, we only release 12 videos. And we ask the participant to predict the future 5-second response based on the last frame. And for our data, we have 8 cameras surrounding a vehicle released. We have eagle stays. We have high-level comment routing. And for the validation, we also released a new label, the RFS label, which is called Richer Feedback Score. So for all the videos, we ask human labelers to label 3 diverse trajectories with a score from 0 to 10. 0 means this is super dangerous trajectory, don't go like that. And 10 means this is good trajectory to go. And then we will compare the prediction with these 3 trajectories to match the distribution and then get a final score. So before I delve into the final list of the winners, I want to say like we really appreciate every participant joining this challenge. A lot of information that we have seen is really insightful. And so our winner is Wolfram from EPFL. And second place is Diffusion Leal-Taixe, which is from University of Tübingen and ASMK and NVIDIA Research. And third place is Swing Trajectory from Hongyang University and Reflex Inc. And we also have a special mention Protein, which achieved very, very high score in the report. And from Mela Kubik AI Institute. And I will leave a stage for Protein to present.
Hi, so we'll be presenting Poutine. We wanted to thank Waymo for this special mention, even though we weren't able to compete due to being from Quebec. This is joint work with Rod and I, as well as our co-authors at the Mila Quebec AI Institute. So what is Poutine? Poutine is a vision language model for long-tail driving. So we trained this vision language model using a larger training corpora than was provided by the Waymo end-to-end training dataset. Specifically, we additionally added this co-VOA dataset, which consists of 83 hours of front view driving in Japan. And to align to the vision language model's language space, we automatically collected language annotations using a large Qwen 72B vision language model. And we specifically instructed the model to output annotations in the following format shown on the right, where it outputs a critical objects list, as well as an explanation and meta behavior that describes the optimal future driving trajectory of the ego. And we followed a simple two-stage training recipe built on top of the Qwen 2.5 Vision Language 3D model. So the first stage is what we call Vision Language Trajectory Pre-training, and this gets us our poutine base model. And this is just standard next token prediction on interleaved vision language and trajectory tokens. And interestingly, we only required the front 3 views of the present frame to achieve strong performance. And the second stage gets us our final poutine model, and this is with RL preference fine-tuning using the GRPO algorithm. And this was fine-tuned on the provided Waymo validation dataset, where we used RFS directly as a reward signal, and we also had an additional format reward for formatting the trajectory properly. So how does poutine perform? So at the end of the submission deadline, poutine significantly outperformed the other submissions, with the model before RL still outperforming the other submissions by a considerable margin.
Several experiments that we conducted as part of the challenge. We did our evaluations on the Waymo validation set. So here we show some comparisons between different pre-training and inference strategies. So the first 2 columns was which of the driving data sets were used during pre-training, either the CVPR' or the Waymo end-to-end driving data set. And then the next 2 columns specifies whether we used generative language annotations during pre-training and whether we did the chain of thought prompting at inference time. So the first interesting result that we found is that we already get pretty good score on the Waymo driving dataset when we only do training on the Japanese driving dataset. So this is without seeing any Waymo data during training. And the next 2 rows, these are experiments that basically showed that both the generative language annotations and the COVID driving dataset used during training gave us overall the best score when we did evaluation on the Waymo driving dataset. And then finally, the last interesting result that we show here is that when we do chain of thought at inference time, we didn't actually see an improvement in performance, which is consistent with other works that have shown this in the past, and indicates that this is still an open area of research. Next, we'll evaluate the impact of our second stage reinforcement learning as part of the poutine pipeline. So for these experiments, we trained on 90% of the scenarios in the Waymo validation set, and then we did our evaluation on the held out test set, where we show the results in this figure here. So from this figure, we can clearly see that our second stage clearly yields strong gains when we do reinforcement learning on our poutine-based model. And the second result that we show here is that when we look at our model that was trained on both the coding and the Waymo driving dataset, and the model that was only trained on the Waymo dataset, we see that the model that was trained on both driving dataset gives us an overall better performance when we do our second stage reinforcement learning stage. And as a final part of our results, we'll show 3 example scenarios where we plot our model predictions shown in green, and you can see compared to the future trajectory of the ego shown in red. So in this example, we see that there's a vehicle that emerged onto a lane from the right, and our model successfully slows down. In this last example, there's an animal that crosses the road, and the model predicts to slow down.
So what are the main takeaways of Poutine? So first is that you can take these public pre-trained vision language models without modification, and they can serve as very powerful general architectures for vision tasks such as end-to-end planning, even if you're not explicitly using language as a modality. We also show that a very simple training recipe of next token prediction pre-training, followed by lightweight RL reference fine-tuning, can yield state-of-the-art planning results on this benchmark. And finally, Poutine requires very minimal human effort, in that no human labor was required to train the Poutine-based model, and reinforcement learning only required around 500 frames of preference-labeled trajectories. Thank you very much.
All right, so now we're going to show a video from the Diffusion LTF team, which was our second place finisher in the end-to-end driving challenge.
Hi everyone, I'm Kashyap. I'm excited to present our solution to the Waymo end-to-end challenge. The AV datasets available to the community today are extremely complementary. On one hand, you have synthetic datasets like Carla that have really precise and diverse annotations, but lack diversity in scenarios and have visual domain gaps to real data. Then we have perception-centric datasets, which have 3D annotations and maps, like the Waymo Open Perception Split or NavSim, where you can learn perception tasks very well, but the data is not curated for extremely challenging scenarios. And you have, on the other hand, the data that was released for this challenge, where there is no annotation, making it extremely difficult to learn models on this data. But the scenarios are really challenging with lots of rare and infrequent events. So our approach is to try to unify all of these data sets into a standardized format for training. We do this in a repository which we call OpenXAV. And one of our goals is to have a simple format that's easily extensible so that we can add other public data sets into this mix for future work. With this repository, we have a multi-stage training pipeline where we pre-train on most of the perception-centric data, where we spend the large portion of our training budget learning tasks like 3D detection, bird's eye view segmentation, and depth estimation. Here, the planning heads or planning task is not trained, and the network focuses on learning good visual representations. After this, we have a very lightweight post-training phase where we fine-tune the entire model end-to-end on the challenging scenarios in the Waymo end-to-end split used in the challenge. So our architecture is based on latent transfuser or LTF, which is a well-established backbone on NavSim and Carla. The main chunk of the architecture is a perception encoder that takes three front viewing cameras as input and generates bird's eye view scene tokens. It also encodes the ego status like the velocity and navigation command, and all of these tokens are concatenated together. Now the standard latent transfuser planning head predicts the waypoints deterministically from these tokens, but our architectural innovation for this challenge was a diffusion-based addition to the latent transfuser architecture. Specifically, we have multiple modes of noisy trajectories, which through a trajectory encoder, which is a self-attention module, are encoded to waypoint queries. And these entire set of status and BAV tokens are used with a transformer decoder to decode these queries into denoised predictions using a standard DDIM formulation and scores for classifying which mode is most suitable for this scenario with a cross entropy loss. So Our final architecture for the challenge actually used a common backbone encoder and two parallel planning heads, both the deterministic latent transfuser and our new diffusion LTF head. And as per the main challenge metric, though both heads independently achieved similar scores, we see that ensembling the predictions of the two heads together gives a boost, which is further increased by drawing more samples from the diffusion decoder. Additionally, we find that pre-training is crucial. So pre-training on any one of the data sets already gives a large boost in performance compared to not pre-training. And in particular, the Waymo open perception split is well suited for pre-training in this challenge. So here are some qualitative results of our method. As you can see, it can handle pretty complicated scenarios in the data set quite well. So this is it from my end. Thank you for listening.
Okay, so before we talk about the rest of the challenges, I want to provide an overview of our perception and motion data sets. The perception data set is comprised primarily of LiDAR and camera sensor data. We also provide labels for various training tasks, including 2D and 3D bounding boxes, key points, and various forms of segmentation. We also provide mapping data in the form of a 3D road graph that you can use to align sensor data with road features. And another feature of the data set is object assets, which are accurately correlated camera and LiDAR observations on a large collection of vehicles and pedestrians. The data set is provided in a modular format, so you can download and work with all the portions that you need. And as I mentioned earlier, the motion data set is suited for prediction and scenario simulation tasks. It features a much larger number of scenes with over 570 hours of driving data collected from over 100,000 driving scenes in 6 US cities. We also provide accompanying bounding boxes produced by an off-grid model and 3D mapping data. Over the last couple of years, we added LiDAR data and camera embeddings to encourage more end-to-end methods. And later this year, we plan to release an update with route information for the Ego vehicle. This is in support of one of our most popular feature requests for Waymax, our Waymax simulator. More on that shortly, to enable new metrics like route progress ratios. Okay, now covering our second challenge this year, the interaction prediction challenge. This is our second time running this challenge. First time was in 2021. The objective for this challenge is to predict the joint future positions of Tim interacting agents for 8 seconds into the future, given the agent's tracks for the past 1 second on a corresponding map. This challenge adds the additional requirement over traditional motion prediction benchmarks that participants must jointly predict the behavior of multiple agents. Here we have an example from the training data set where there are 2 vehicles making unpredicted left turns, where both of them need to wait for the other vehicle before proceeding. The task is to use the first 1 second of this data as agent history, and then predict the trajectories of the interacting agents for the remaining 8 seconds. All right, and the challenge is to, jointly predict the trajectories and there are confidences for the 2 given agents in the scene. Up to 6 trajectory pairs can be predicted per example. And so here you can see we have the 3 predicted trajectory pairs for the 2 vehicles. We updated our interaction prediction benchmark last year. So this is the first year for us running the challenge with soft mean average precision, or soft MAP, as the evaluation metric. The soft MAP design addresses the multimodal nature of trajectory forecasting. So that's how it works. First, we classify each ground truth trajectory into one of 8 behavior buckets, such as left turn or right turn, and one of 3 object type buckets. And then next, we evaluate the model's predictions. And prediction is considered a true positive if its path is within a certain tolerance of the ground truth. These tolerance thresholds are dynamic. They scale with both time and the object speed to account for increasing uncertainty. The soft component of the metric is crucial. It does not penalize the model for generating multiple valid predictions for a single agent. This intentionally rewards models that can capture the inherent uncertainty in a traffic scene, where several future paths may be plausible. And finally, the overall performance is quantified by computing the mean average precision over all the behavior and object buckets. This aggregation gives us a single robust score that reflects the model's overall predictive capability. So it's my privilege to announce the winning teams from this year's Interaction Prediction Challenge. First, I want to thank all the participants in this year's challenge. We had some really strong participants, and we appreciate all the hard work that went into it. Third place team with method name B-Top Ensemble achieved a soft MAP score of 0.2573, and our fourth place team, Retro Motion, achieved a Vince score of 0.2562, which earned them as an honorable mention for the challenge. And I think Raiden from the Retro Motion team is actually here with us. All right, and then in second place was the impact method. And in first place, the parallel mode seek, which achieved a very staggering 0.2978 score on our soft MAP metric. So we'll now hear from the parallel mode seek team on their method.
Hi everyone, I am Zhan. In this talk, let me introduce Parallel Mode Seek, our solution to the Waymo Interaction Prediction Challenge. Anticipating the multimodality of future events lays the foundation for safe autonomous driving. To this end, we need to capture the full distribution of agents' future. However, only one possibility can be observed in real-world driving data, which makes multimodal behavior prediction challenging. Our framework for multi-agent behavior prediction comprises a scene encoder and a trajectory decoder, which encodes robust traffic scene representation efficiently and decodes multi-agent trajectories in consideration of multimodality and scene consistency. We adopt the query-centric encoder proposed in our work QCNet, which encodes viewpoint invariance, input embeddings, and relative spatial temporal position embeddings, fusing the scene context using relative position-based transformers. To learn multimodal behavior of agents, most prior works adopt the paradigm of set prediction, where the modes are unaware of each other or their relationships are weakly modeled. Moreover, these methods employ the winner-take-all training strategy, suffering from limited trajectory diversity and uncalibrated mode confidence. As a remedy, some recent works opt for dense mode prediction followed by heuristic mode selection. Despite their improved trajectory diversity, they often produce low-quality trajectories. In particular, the anchor-based approaches under this paradigm fail to scale for joint multi-agent prediction, since the combination of dense anchors from multiple agents is exponential. In contrast, our work ModeSeek published in this year's CVPR models modes as sequence, which captures the relationships between modes by reasoning about the next mode step by step, conditioned on the previous modes. This method has improved trajectory diversity, calibrating mode confidence, and good trajectory accuracy under the paradigm of sparse mode prediction. However, ModeSeek relies on recurrent mode generation, which is too slow for real-time prediction. For this reason, we developed a parallel version of ModeSeek. In parallel ModeSeek, we translate the mode set into a sequence via causal mode-to-mode attention, and then leverage transformers' capability of parallel decoding to predict all modes in parallel. We also stack multiple layers and apply training losses to each layer for iterative refinement. In between decoding layers, we employ an operation of mode rearrangement to prioritize the refinement of the more probable trajectories in the next layer. To perform multi-agent joint prediction, we follow our work QCNet to add a future interaction transformer that can improve the scene consistency. Moreover, we achieve scene-level mode scoring via max pooling over all target agents embeddings in the scene. As for training, we propose the EMTA loss to replace the popular winner-take-all loss, in which we optimize the match mode decoding at the earliest step in the mode sequence. We found that our EMTA training strategy results in better mode coverage and confidence scoring without significantly sacrificing trajectory accuracy. The training loss consists of 3 parts, including the regression loss based on the Laplace negative log likelihood, the classification loss based on the binary focal loss, and the margin ranking loss aiming at minimizing the average number of confidence inversions in each training batch. Our model has 11.2 parameters. Without employing tricks like model ensembling or dense mode prediction followed by non-maximum suppression, parallel mosaic outperforms other submissions by a large margin, which demonstrates the advantages of our overall framework. To summarize, we create a new path to solving multimodal problems, including a mechanism of sequential multimodal decoding, an architecture of iterative refinement with mode rearrangement, and a training strategy of EMTA label assignment. Thank you for listening.
Thank you, John. I'm Reza Majurian from Waymo, and I'll be presenting the sim agents and scenario generation challenges and their results for this year. So before we dive in, we thank all the participating teams for all the great work and all the submissions that you've sent us. We rely on simulation for testing the autonomous vehicle software on diverse scenarios and rare scenarios that may not come up often in the real world. The sim agents framework gives us the ability to simulate these diverse scenarios and test the AV software. In this challenge, the inputs include agent history and scene data over 1 second, and the objective is to generate 32 realistic rollouts of the scene with 8-second future trajectories for all the agents. So the model sees where all the agents have been for the past 1 second, and then it comes up with new futures for these agents that are present in the scene. Next slide, please. To better motivate the sim agents challenge, we can take a look at a motion prediction model. This is a challenge that we have run for the past 4 years, but we're not running it this year. But if you look at such a model, this model predicts trajectories and associated scores for each agent. These predictions can be used by the onboard software to create a motion plan for the autonomous vehicle, but they cannot be used for simulation. If we just sample from these predicted trajectories, we might end up with agent behaviors which are not mutually consistent, and that will not yield a realistic scenario. We just saw how the interaction prediction challenge focuses on this problem by expecting consistent trajectory sets from a pair of agents. The sim agents challenge takes this to the next level by requiring a set of consistent trajectories for all the agents in the scene. Next slide, please. So we evaluate the submissions by compiling a distribution of simulated behaviors for each agent and then comparing those distributions with the ground truth behavior of that agent. For each agent, these distributions capture the agent's motion profile, how well it follows the map, and how it interacts with the other agents in the scene. The final metric is a weighted average of all the metrics in these 3 categories. Next slide, please. With that, I would like to introduce the winners. In first place, you see Traj Talk from Shanghai Jiatang University. In second place, you see RLFD Sim from University of Alberta and York University. And in third place, we have Combot from Cognibit. An honorable mention goes to UniMM, that's short for Unified Mixture Model, from Zhejiang University and Horizon Robotics. Next, you'll hear a 5-minute video presentation from Traj Talk.
Hello everyone, I'm Zhiyuan Zhang from the Think Lab of the Shanghai Jiaotong University. In this talk, I will introduce TrajeTalk, a trajectory tokenizer for discrete token prediction-based behavioral generation models. Behavioral generation is an important component of autonomous driving simulators. Recently, inspired by large language models, a series of behavioral generation models adopts the next token prediction (NTP) paradigm such as Leal-Taixe and SMART. This model tokenizes agent Leal-Taixe of a certain interval into discrete tokens and predict probabilities for each token. Then select the best trajectory token for the next interval. There are two types of trajectory tokenizers in NTP behavior generation models, the data-driven methods and the rule-based methods. The data-driven methods process trajectories in real world with classical or other algorithms, such as the k-disks. Rule-based methods directly generate the vocabulary without the data. In this work, we conduct an analysis of what makes a good trajectory tokenizer in behavior generation and propose the trajectory tokenizer. This figure shows the trajectory vocabulary generated by the k-disk tokenizer and our trajectory tokenizer. Each color line represents a trajectory token with 0.5 seconds in agent-centric coordinate system. The token generated by k-disks is asymmetric and there are some batch trajectories, while the tokens generated by trajectory is symmetric and has a high quality. In the top right image, orange dots indicates the endpoints of the tokens, and the blue dots indicates the endpoints of real trajectories in the dataset. Compared to k-disk, trajectory has a wider coverage. Trajectory generates the token with 4 steps. First, we extract all valid trajectories of a certain length in the dataset and normalize to the agent-centric coordinate system. The trajectories are copied and flipped along the x-axis to ensure symmetry. Second, we generate the grid with a predefined range and interval. Each trajectory is associated with a cell. If its endpoint found with the cell with trajectories associated is colored in orange in this figure. We can see that there are some abnormal points far away and some holes. Third, for each cell, we compute the numbers of cells with trajectories around it with a binary map. In this way, we filter the abnormal points for the holes and expand the border. Finally, we generate a trajectory token for each valid cell. If there are trajectories associated with the cell, the token is generated as an average. If not, we generate the token with the curve interpolation. The generated trajectory vocabulary can be used in various NTP behavior generation models. We also improve the token-related designs. We propose a special aware label smoothing method for cross-entropy loss used in the NTP behavior generation model. Standard label smoothing assigns a sub-target probability to each non-ground truth token, while we assign a larger probability to tokens that are specially close to the ground truth and give a smaller value to tokens that are far away. This special aware label smoothing can both reduce the errors and improve generalization. We use the Smart Tiny model as a base NTP behavior generation model. We replace the k-disk tokenizer with trajectory and use a special aware label smoothing method for loss. Compared with the baseline, our method greatly improves the performance and ranks second on the leaderboard. In this study, we found that a good trajectory tokenizer should be well in coverage utilization balance, symmetry, and robustness. For coverage and utilization, the tokenizer should cover trajectories that do not appear in the dataset but may occur in reality, and avoid including too much invalid trajectories. For symmetry, considering the symmetry of vehicle kinetic models, the diversity of real-world traffic scenarios, and the left-hand and right-hand traffic routes in different regions, generally the possible ratio of the trajectories is symmetric. For robustness, the tokenizer should not be easily influenced by noise in the dataset. You can find more information in our technical report. Thank you for listening.
Thank you to the Trash Talk team. We also have an update to share on Waymax, which is a lightweight research simulator developed by Waymo for solving sim agents and planning problems. Waymax is written entirely in JAX, so it's differentiable and hardware accelerated. The code base was recently updated and you can check it out on GitHub. Next slide, please. Next, you'll see an overview and the results from the Scenario Generation Challenge, which is a new challenge introduced this year on the Waymo Open Motion dataset. So this challenge extends the sim agents challenge, which we just saw. In that challenge, all the agents are given and only their futures are generated by the models. In the scenario generation challenge, there are no input agents. All the agents besides the AV are generated by the models. The only inputs to the model are the scene map and a 1-second history for the ego vehicle. The model is also told how many agents to generate for each type. For example, a scenario might ask for 15 vehicles, 8 pedestrians, and 1 cyclist. The models are then expected to generate 32 full instantiations of the scenario, which requires generating initial agent positions, bounding box dimensions, and full 9-second trajectories for the requested agents. So the outcome is that you have created a stronger tool for generating diverse driving scenarios, and this can better test the AV software in novel situations. The scenario generation metrics are also an extension of the sim agents metrics. In the sim agents challenge, behavior profiles are created and scored for individual agents, but in this challenge, we generate and score collective distributions from all the agents present in the scenario, and we compare that with the ground truth. With that, I would like to introduce and congratulate all the winners in the first round of this challenge. The winners are SimFormer from Shenzhen Urban Transport Planning Center, UniTSG from Tongji University, Yanshan University, and Xi'an Technological University. And in third place, you see Shred from University of Tübingen and NVIDIA Research. Lastly, honorable mention goes to InfGen from UCLA. You can check out the tech reports from all the winning teams for all the challenges on the workshop website. Next, you'll see a short video by the winning team, SimFormer.
Hello everyone, and thank you for being here. I'm Sun Wang, and today I'm excited to share with you SimFormer, the system that earned first place in the Waymo Open Scenario Generation Challenge 2025. Let's dive into how we achieved this milestone. Rule-based and simulator methods like Sumo and Carla rely on predefined traffic rules or microscopic simulation engines to synthesize scenarios, which result in lacking of realism and diversity, especially for rare events. On the other hand, regression-based approaches model agent positions, attributes, and trajectories as continuous variables, typically regressing to real-world distributions using neural networks. While effective for basic realism, such models face challenges in diversity, scalability, and efficient generalization. Recently, discrete tokenization and autoregressive methods have shown strong promise. Inspired by language modeling, these approaches convert continuous scene elements and trajectories into discrete tokens and leverage GPT-style transformers to predict token sequences. This enables scalable, flexible, and generalizable multi-agent scenario synthesis. First of all, we come to the problem formulation. The inputs include a high-definition map segment, the 1-second history of the ego vehicle's motion, and the expected number of agents to generate for each type. Given that, it is to generate a set of non-ego agents and their full trajectories over a fixed time horizon time steps. Each agent is characterized by its type, initial position, heading, and 3D bounding box dimensions. A trajectory is composed of center positions and heading angles over time. The number of generated agents per type must match the provided count. In SimFormer, this problem is approached by autoregressively generating discrete tokens that represent agent types, placements, attributes, and full trajectories, conditioned on the map context, ego history, target agent type counts. For the input preparation, we vectorize the map and extract relevant polyline and context features. This input is encoded into fixed-length token sequences to serve as the conditioning context. In the tokenization step, all agent-related elements, including initial positions, physical attributes, dynamic attributes, and trajectory fragments, are discretized into interpretable token vocabularies via clustering or binning techniques. Next, SimFormer iteratively generates agents in a grouped and type-aware manner. For each agent, it sequentially predicts an agent type token, a position token, attributes tokens, and a sequence of trajectory tokens. Finally, the generated tokens are mapped back to continuous representations, recovering full initial states and 91 time-step trajectories. These are then serialized into structured outputs for evaluation and submission. Dive into the tokenization strategies. There are 3 key points. For the initial position tokenization, we firstly represent each agent's location relative to the ego vehicle's local coordinate frame to capture the spatial distribution of non-ego agents. And then we apply clustering to these relative positions across the training set to obtain a finite set of representative position tokens. Therefore, what the model predicts are the relative position distribution relative to the ego vehicle. This tokenization strategy allows flexible and scalable modeling of complex multi-agent spatial layouts. For the tokenization of physical and dynamic attributes, we discretize that into 2 separate joint token vocabulary to improve efficiency and capture correlations. The agent's length and width are jointly discretized. And the agent's initial speed and yaw angle are jointly discretized. Each size token corresponds to a bin in a tailor-dimensional space. Therefore, what the model predicts are probability distributions over these 2 attribute token vocabularies, which enables to cover the real-world agent attribute distributions. Finally, to efficiently represent agent motion, we follow SMART's approach by segmenting trajectories into fixed-length intervals and applying clustering to build a trajectory token vocabulary. Moreover, we employ a reverse matching strategy to ensure that the first token is physically consistent with the agent's given initial state. To summarize, here is an overview of the tokenization strategies. SimFormer constructs all token vocabularies from training data. Position tokens are obtained via clustering on ego-relative coordinates, while size and dynamic attributes are discretized through uniform binning. Trajectory tokens are derived from clustered motion fragments. We discretize the task by clustering trajectory data into 4 token types: position, size, dynamic, and trajectory, and employ a dual-stream transformer for prediction. The architecture consists of a 3-layer map encoder and a 6-layer token decoder, where map features are first processed through shared layers before autoregressively decoding agent tokens. Now, we will show the details of implementation. The left table is the configuration for training process. The right table shows the parameters for clustering and discretization algorithms. Here is the model result, following the official Scenario Generation Challenge 2025 data splits and evaluation protocols. Here is the method comparison result. SimFormer demonstrates superior realism and diversity across all key metrics. In conclusion, we presented the model named SimFormer. The technical innovations to highlight are well-architected tokenization strategies and a scalable autoregressive architecture. The experiments on the Waymo OpenMotion dataset show the model ability to capture the complexity and diversity of real-world traffic. Please allow me to introduce myself. I am Sun Wang, an AI engineer at Shenzhen Urban Transport Planning Center, specializing in 3D machine learning, computer vision, and multi-agent systems. At SUTPC, a global leader in smart mobility solutions, I focus on innovating intelligent transportation technologies. Feel free to connect via email or visit my GitHub to explore my work. Looking forward to exciting discussions.
So Tina, we published 16 technical reports from our incredible field of participants on our website or shop on Cloud Strategy website. We encourage you to go ahead and check them out. And lastly, I want to acknowledge the team that made these data sets and challenges possible this year. This year's release was the most ambitious yet. It's a large team of passionate engineers and researchers who look on this ambition to do other duties to pull it off. And effort will only possible thanks to some contributions from teams all across Waymo.
Okay, thanks, Ariel.
So first of all, I'm Xianming. I'm from Expo. So I'm leading the IT at the Autonomous Driving Center. So today, probably I will talk about something different because I'm probably the only one from the massive production vehicle company. So first of all, let me introduce who we are. So we are Expo. We build cars. We also build autonomous driving softwares. We build everything from end to end in our own staff. And most importantly, we are one of the AI-based companies, so we develop everything based on AI models. So first of all, let me just try to show what we do. So first, all the videos is from all the massive production vehicles we directly shipped to consumers, not as something demos or not something experiment. Oh, sorry. In this video, we just show the safety functionality of the vehicle we shipped recently, last week, including weathers, fogs, waters, and also sometimes you see the small dogs, small debris in a very dark environment. And if you work on the home driver, you will see the debris, like the tires, is pretty annoying. It's pretty difficult to discover the obstacle in the dark environment and also trying to make a maneuver. Yeah, this is a small dog in the very dark environment. Only highlight is enabled. All the vehicles we deliver doesn't have lidars. We don't have the cameras and radars. So all the stack you see here depends on the cameras. You see here, this is one of the challenges I like most. This is small debris. If you work for the both companies, you will see this is a pretty challenging because it's very small, and you have to make a decision whether or not you want to yield. Okay, here you go. So here lists some of the capabilities we shipped to all of our customers' vehicles, including very competitive lane change. This is very common in China. If you drive in an urban area, dense urban area, you feel it's pretty challenging to make a lane change. You need to compete with the other agent to make a lane change successful. And this one, I don't want to show it. For this one, this is a navigation in the urban area, in the very narrow street, use a double point vehicles outside. And also there's a lot of VRDUs coming across. And the last one is very interesting. So, this one, the first one. Even we don't have any navigation, which is in campus, we can still drive. This one, because all the stack is not placed, that means we don't have any high-definition app. We don't have navigation and cameras. And so it enables us to drive through the constructions even though there's no road. You can see this is no road. There's no definition about road boundary or lanes, nothing. There are also some construction debris on the ground. The vehicle can still make the lane change or make the maneuver. Okay, here you go. So one is to try to recap what we experienced in the past decade for the autonomous driving software. So 10 years ago, everyone is busy with something of Deva challenge, where you rely on a lot of lidars using the point cloud with the clusters in CPU and detect a worse object or worse obstacles, and writing a lot of hard-coded heuristic SQL oscilloscope to make the maneuver. So in this case, the entire stack is defined by simple oscilloscope. We call it software 1.0. So maybe 6 to 7 years ago, when detections or computer vision becomes more and more matured, people started replacing the perception and prediction using the machine learning models. But still, I think majority part of the stack is still C++ with certain part replaced by well. And software 2.0 is very famous because it's proposed by Envy. That means if we want to iterate on software using data, you have to convert the entire software into AI models and try to do iteration based on the data-centric. So from here, people say it's a AI models as a software. So currently we are at the stage where we build everything based on end-to-end AI models to drive the car. So for the next stage, we need to explore what we're going to in future. Based on scaling law, like everyone is going to expect scaling law. So some people say scaling law is that because we don't have enough data, but actually for AV companies or for the up-drive vehicle companies, we're not linked to the data. We are not linked to the data, so it encourages us to think about how we can move forward in the massive scale, where we can collect data from the real world using hundreds of thousands of vehicles. We collect a lot of data every day, and then we train a very large vision models as a factory. So once you have this, you can distill the model into a smaller vehicles, smaller hardware on the vehicles. So we define this prototype as a software 3.0, but the name is so here the philosophy is once you can solve the problem using large scale foundation models, regardless of the prior data scales and tree data scales, so we can always deploy the model onto the on-device environment. And then the problem becomes deployment problem, including protein quantification, distillation, and also building better on-device hardware. So this is the philosophy we are aiming for the next generation. So in order to build something like this, we create tools. Inner loop is we pre-train a foundation model using the scale data, and then do the reinforcement and SFT post-train to keep improving the model performance. And lastly, we do the distillation to squeeze the model into smaller ones and deploy the car. This is the inner loop, how we just iterate one circle. And that circle's outer loop. As I said, once we deploy model to devices, we have hundreds of thousands of vehicles as a sampler in the real world. Sample data keep continuing training. So we define some outer loop where we continue training, or some people would say it's called online training. So we keep iterating like this until calculate the performance is good enough for L3 or L4. So I will talk a little more about why we need close training. Essentially reinforcement learning. So imitation learning can never achieve L3 or L4 because there's a lot of corner cases you see from Waymo graphics card. Like there's a lot of corner cases you can ever achieve by imitation learning because you don't have the data, or you don't have this to avoid the collisions or corner cases. So reinforcement learning can provide another solution where it can solve the corner cases. I will talk more later about this one. Here is how we train the model. We can divide the stages based on different perspectives. First one, you can divide it by pre-training alignment, which is a beyond model pre-training, and then actual training. That means you build an actual net, try to train actually for, and then SRT, which is a super expansion to the instructor following, and then lastly, reinforcement learning. Or you can divide it based on the input and output models. The first model here is includes the image and text pairs. So here we just train the correlation by doing images and languages or knowledge. The second part is we input the videos and actions. We want to model visual actions. It's just class learning. And lastly, during the reinforcement stages, includes just video sequences and reward. We don't want to use actions as a creation to boost the performance of the model itself. So this is the second perspective design. And third perspective is actually we can divide in the middle. So here is pre-training, and here is post-training. So this is how we define the stages. I will talk about stages. About how stages work. So this is a model architecture for foundation models, especially forward using VNG as a encoder. Interactive camera was a Dataset prompt into the tokenizer and into the LNF at the going the actually generator, including visually CVT, and finally come to a stage of the reinforcement. And finally, we almost upload the 600 terabytes data into our cluster. So even though we are showing a very extensive result to show the schedule, but we still can see something from it. once we increase the model size from 1 million to 3 billion, 7 billion to 32 billion, the ADE metrics keep decreasing and almost showing sub-billion scale. And the other one is once we increase the data volume from 1 million to 10 million to 14 million to 40 million, we still see the metric decreases very sharply. So as long as for now, once we increase the model capacity and data scales, we haven't seen this one being separated. So this gave us the confidence to move forward with training an even larger model. Firstly, I will talk about environment or the data injection and goal injection. So in order to do this, we compose our data from like this. So in the last round of data, we are using 50 million video and text cards to train this stuff, to inject knowledge into our viewing models. And the master version of our version right now, we consume 160 billion training data samples. So this shows some example of the data. The left one is TSL, the history of the vehicles who want to the model to answer a question like what is the status of vehicle, and on the right side probably it is the traffic light. Now when we want to detect the traffic light status, one also want to ask a question like whether or not this traffic light control your lane. What this step is doing, we also trying to do the supervised learning SRT to enable the safety for the COT. This is one of very important step because a lot of us use simulations. It's very complicated. It's pretty straightforward. It's pretty hard to do it. Say once you see the scene with the overall actions. Sometimes you need more time to thinking. So that's why we enable train the COT. First COT is a description of the environment, reasoning, next steps, actions, and finally the trajectories. I don't want to go too much detail about this one, but we divided the training into 4 stages, including alignment, to give you the basic knowledge about where a cycle is the train, COT, SFT, secret fine-tune to enable the CFT. And we also introduced the reinforcement to do the COT, the fine-tuning as well. And lastly, because we cannot run the COT or have the cars pretty heavy, we have to reduce the COT to avoid the CT where we reduce rotation. And that's the thing is, so you can see from here is action-based here. Means we still need to output with the action will look like. The action is not some language of text output, it's described, it's virtual token. We divide the actions into longitudinal action, like lateral action, including accelerate, decelerate, speed up, make left turn, right turn, or change of stuff like this. So everything like this is derived from the trajectory look like from a vehicle. And lastly, I see something interesting from what we got from the COT and mind action. So here, each kind of is one to call raging area or passage area, where the moving street traffic light is green and left turn traffic light is red. You have to move into the channel and wait in the waiting area. So the COT, after the COT training, you can see the hover trajectory can directly ask the car to go into the waiting area without too much other boost. And we can also control the COT output to make the vehicle to output different trajectories. For example, here, if we change the traffic light from right to green, the vehicle will move forward. So this is pretty important because we needed this COT and mind action to generate something we can use once in the facility. And here also shows some interesting results over on the meta actions. So in this mind action, the default of the chooses the vehicle move straight, as we are. And we can always change the mind action to see how the vehicles move. Here we can move we can change the mind action that's speed up, changing lane to change the right lane, or stay in the lane. You can see your trajectory changes accordingly. And you can also ask the vehicle to slow down. The vehicle can reduce instead of the becoming denser. And here is changes eventually without too much vehicle pressure. the vehicle can achieve the action to achieve the right lane. And finally, this one is even more interesting. So once there's a lot of vehicles on the right lane, and you ask the vehicle to change lane to the right, the vehicle stay in the lane. Because there's 20 vehicles on the right side, you cannot leave a change. So this is the first stage, alignment and COG. The second stage we do is superstructuring. There's a lot of challenges in evaluation learning where evaluation learning only learns statistical mean of the already we have. Sometimes we can learn about probabilities to probably know what this fusion agent also, for example, forward navigation and make a very comfort break or something else. So we model this as a we model the SRT as a kind of a instruction following steps. So here is we curate the data, do the data curation to get a bunch of casting data we want to use in SRT stage, and we construct the key information prompt and formally we characterize as a instruction following. Here shows one example how the instruction following works. This is navigation. We ask the vehicle to follow the GPS, follow navigation to change lane into a maneuver or make a left feature and then make right turn. And then we use SFT to teach them all. You should follow this one. So this is a very straightforward instruction forward task, and the solution is very straightforward as well. It's using SFT. Here shows an example as well. What do we do in the FSG stage? Equal to traffic light, intersection W, and navigation lane change called an LC. For example, you want to make a lane change to the left lane, so you can make a left feature in that intersection. And here's a highway Wolfram of highway or get off the highway going to the ground. It's also instruction following. And the final way for comfort rating. Comfort rating is not so straightforward, but it's still some kind of instruction following. You want a vehicle to stop comforting. We got very high bake, and you can give the bottom a lot of examples what is defined as comfort and what to follow. And lastly, tap to the reinforced learning. This is very tricky. So before we go into reinforced learning is something you have to build a reward model or word model and do the reward matching, do the reinforcement learning. Yeah, everyone follow the same thing actually. Eventually for how driving is that the hardware becomes safer. To do the reinforcement learning, to drive safer, you probably just need 3 higher for reward. Safety heart rate. Second one, efficiency. You don't want to be stuck. And you don't want to drive slow on the 60 miles per hour lane. And also you want to follow the compliance of the traffic rule, like traffic light, lane change, or the others. So the real virtue will be very straightforward to define. After applying your functions, using your figure out itself, since we can achieve critical result. I'll show you demos. This one is user, maybe user. On the left is something we didn't apply reinforcement learning. You can see the vehicle trajectory calculated with the boundaries, and it's not very stable. On the right side, it's after reinforcement learning. The vehicle knows how to decelerate and how to make sure the trajectories are smooth and don't pollute us with the low boundary. And this one is also on the left side. After SFT, the model is very eager to move forward without keep the very safe distance with the VRU. And on the right side, the model can learn we should yield to the VRU on the safety distance and then move forward quickly. This is the similar issues. On the left side is something before the reinforcement learning where the model does about how you yield to appeal. And on the right side is after the reinforcement learning. Okay, so to conclude the summary, what we do is we try to explore the new pattern developing AI models for autonomous driving. So first of all, it's the data-centric. The internal pipeline defined by the data. So scale data through large foundation models to achieve better performance continuously improving by daily iteration. So this is the first change. The second one is
we wanted to change the model development cycles of patterns from pre-training to quality to distribution to completed the whole cycle. And thirdly, keep doing this spontaneously online to receive the data and deploy the model to sample more data and capture the model itself. And lastly is we call it software 3.0 cloudly. After today, everyone should remember that thing, the 3.0, which is to train a large model, distill or deploy to smaller one some device, and then forward. And some work we are going on, including deployment. We calculate everything based on the foundation model right now offline. And currently we are deploying this model to our commercial vehicles, consumer production vehicles. The second one we're working on is to keep making the alternative work contain a solid area. And thirdly is the learn model. Learn model is not only doing the 3D reconstructions, but it's more once you give symbol to the model, and the model should give you a word, and more about imagine rendering that. So hopefully next year I can just present you can work see. Finally, to conclude on, let me show some demos directly running the model on high to experience how it works. The first one, sorry, with the build quality is not too good. So minimum number lane change to avoid the dark parked vehicle on the road. Second one is a pretty dense urban area. There is a lot of traffic, so you can see our very first floor traffic. And some traffic is blocked in the middle of the way. You need to move the door to the right. And there's a lot of vehicles. Model didn't have any heart rate and no collisions, no rules, no symbol like the Sigma must go, just use the model inference. Very controlling the code. And after that, you have to do road selections of the road. And this one is go through the construction area. I think there's some construction costs here. If you work on off-road or home driving, probably general addition of the construction costs is one of the big problem facing now. And the model right now here had pretty well. And lastly is we didn't have enough picture. Even there's a vehicles and there's some very use on all the direction. And you have to make a yield and move forward. In the third process, you can see from the curvature of the acceleration, there's no heartbreak. So you will feel very comfortable about that. Okay, I think the summer is tough. Thanks everyone.